communicate verbally, but in the attempt to talk around it. Eastern literature speaks repeatedly of dancing energy and transient impermanent forms. This is strikingly similar to the picture of physical reality emerging from high-energy particle physics. Buddhist literature does not speak of learning new things about reality, but about removing veils of ignorance that stand between us and what we already are. Perhaps this accounts for the fact that the preposterous claim that mass is only a form of energy is unexpectedly palatable. The formula which expresses the relationship of mass to energy is the most famous formula in the world. E equals me to the energy contained in a piece of matter is equal to the mass of the matter multiplied by an extraordinarily large number, the speed of light squared. This means that even the tiniest, the very tiniest particle of matter has within it a tremendous amount of concentrated energy. Although Einstein didn't know it at the time, he discovered the secret of stellar energy. Stars continuously convert matter into energy. It is because of the very large ratio of energy released to matter consumed that stars can continue to burn through countless millennia. At the center of a star, hydrogen atoms, the primordial stuff of the physical world, are squeezed together so tightly by the enormous gravitational force of the star's dense mass that they fuse together, making a new element, helium. Every 4 hydrogen atoms become one helium atom. However, the mass of one helium atom is not the same as the mass of 4 hydrogen atoms. It is slightly less. This small difference in mass is released as radiant energy, heat and light. The process of fusing lighter elements into heavier elements is called, of course, fusion. The fusion of hydrogen into helium causes a hydrogen explosion. In other words, a young, burning star. 156 nonsense literally is one huge, continuously exploding hydrogen bomb. The formula E equals me2 also resulted in the atomic bomb. Atomic bombs and atomic reactors obtain energy from mass by the process of fission, which is the opposite of fusion. Instead of fusing smaller atoms into larger ones, the process of fission splits atoms of uranium, V/H are quite large into atoms which are smaller. This is done by firing a subatomic particle, a neutron, at an atom of uranium. When the neutron hits the uranium atom, it splits it into lighter atoms, but the mass of these smaller atoms together is less than the mass of the patent atom of uranium. The difference in mass explodes into energy. This process also produces additional neutrons which fly off to strike other uranium atoms, creating more fissions, more light atoms, more energy, and more neutrons. The whole phenomenon is called a chain reaction. An atomic bomb is an uncontrolled chain reaction. A hydrogen fusion bomb is produced by detonating an atomic fission bomb in the midst of hydrogen. The heat from the atomic explosion, in place of the heat of friction caused by gravity, fuses hydrogen atoms into helium atoms and releases heat in the process, which fuses together more hydrogen atoms, releasing more heat, and so on. There is no limit to the size of a potential hydrogen bomb, and it is constructed from the most plentiful element in the universe. For better or worse, a major revelation of the special theory of relativity is that mass and energy are different forms of the same thing. Like space and time, they are not separate entities. There is no qualitative difference between mass and energy. There is only mass knerd mathematical K. This discovery meant that the two consia /ation la /vs of mass and energy could be replaced by a single consa /ation law of mass entropy. A conservation law is a simple statement that a quantity of something, whatever it may be, never changes no matter what happens. For example, suppose that there were a conservation law /v governing the number of guests at a party. If such a thing were true, we would notice that every time a new guest arrived at the party, some other guest would leave similarly. Every tune a guest at the party left, another one would as us hydrogen becomes exhausted, a star begins to lose the helium at its core. Helium region is hotter than hydrogen fusion and produces heavier elements, such as neon, oxygen and argon, where in turn becomes the solar fuel as its helium becomes exhausted. Special nonsense /157. The rate of guest turnover at the party might be great or small, and the guests might arrive and depart singly or in groups, but in all circumstances the number of guests at the party would remain the same. The conservation law concerning energy says that the total amount of energy in the universe always has been and always will be the same. Weight can convert energy from one form to another, like mechanical energy to thermal energy /IA friction, but the total amount of energy in the universe does not change. Similarly, the law of the conservation of matter says that the total amount of matter in the universe always has been and always will be the same. We can convert matter from one form to another, like ice to water or water to steam. But the total amount of matter in the universe does not change. When the special theory of relativity combined mass and energy into mass energy, it also combined the law of the conservation of mass and the law of the conservation of energy into the law of the conservation of mass energy. The law of the conservation of mass energy says that the total amount of mass energy in the universe always has been and always will be the same. Mass may be converted into energy and energy may be converted into mass, but the total amount of mass energy in the universe does not change. The sun, the stars, even wood burning in the fireplace, i.e. examples of mass being converted into energy. Physicists who study subatomic particles are so familiar with the concept of exchanging mass for energy and energy for mass that they routinely designate the mass size of particles in terms of their energy content. In all, there are roughly 12 conservation laws. These simple laws are becoming more and more important, especially in high-energy particle pH /6, because they are derived from what physicists now believe to be the ultimate principles, latest dance, governing the physical world. These are the laws of symmetry. The laws of S/symmetry are pretty much what THEV sound like. Something is symmetrical if certain aspects of it remain the same under varying conditions. For example, one half of a circle mirrors the other half, no matter how we cut it. Regardless of how we turn a circle, the right half always mirrors the left half. The position of the circle changes, but its symmetry remains. The Chinese have a similar concept, perhaps the same. 158 nonsense. One side of a circle is called yin and other side is called yang. Where there is yin, there is yang. Where there is high, there also is low. Where there is day, there also is night. Where there is death, there also is birth. The concept of yin-yang, which is really a very old law of symmetry, is yet Another way of saying that the physical universe is a whole, which seeks balance within itself. The irony of the special theory of relativity, as apparent by now, is that it is not about those aspects of reality that are relative, but about those aspects that are not relative. Like quantum mechanics, its impact on the assumptions of Newtonian physics was shattering. Not because it proved them wrong, but because it proved them to be quite limited. The special theory of relativity and quantum mechanics have propelled us into unimaginably expansive areas of reality, areas about which we literally had not one previous idea. The assumptions of Newtonian physics correspond to the clothes we always thought that the emperor was wearing, a universal time whose uniform passage equally affects every part of the universe, a separate space, independent though empty, and the belief that there exists somewhere in the universe a place which stands absolutely still, quiet and unmoving. Every one of these assumptions has been proven untrue, not useful, by the special theory of relativity. The emperor wasn't wearing them at all. The only motion in the physical universe is motion relative to something else. There is no separate space and time. Mass and energy are different names for the same thing. In place of these assumptions, the special theory of relativity provides a new and unified physics. Measurements of distance and duration may vary from one frame of reference to an other, but the space-time interval between events never changes. For all this, however, the special theory of relativity has one shortcoming. It is based on a rather uncommon situation. The special theory of relativity applies only to frames of reference that move uniformly, relative to each other. Most movement, unfortunately, is neither constant nor ideally smooth. In other words, the special theory of relativity is built upon an idealization. It is limited to and premised upon the special nonsense /159 special situation of uniform motion. That is why Einstein called it the special or restricted theory. Einstein's vision was to construct a physics that is valid for all frames of reference, such as those moving with non-uniform motion, acceleration and deceleration, relative to each other, as well as those moving uniformly relative to each other. His idea was to create a physics which could describe events in terms of any frame of reference, no matter how it moves relative to any other frame of reference. In 1915, Einstein succeeded in achieving the complete generalization of his special theory. He called this achievement the general theory of relativity. Chapter 1. General nonsense. The general theory of relativity shows us that our minds follow different rules than the real world does a rational mind, based on the impressions that it receives from its limited perspective, forms structures which thereafter determine what it further will and will not accept freely from that point on. Regardless of how the real world actually operates, this rational mind, following its self-imposed rules, tends to superimpose on the real world its own version of what must be. This continues until at long last a beginner's mind cries out, "This is not right, what must be is not happening. I have tried and tried to discover why this is so. I have stretched my imagination to the limit to preserve MV belief in what must be. The breaking point has come now. I have no choice but To admit that the must I have believed in does not come from the real world but from my own head. This narrative is not poetic hyperbole, it is a concise description of the major conclusion of the general theory of relativity and the means by which it was reached. The limited perspective is the perspective of our three-dimensional rationality and its view of one small part of the universe, the part into which we were born, the things that must be other ideas of geometry, the rules governing straight lines, circles, triangles, etc. The beginner's mind was Albert Einstein's. The long-held belief was that these rules govern, without exception, the entirety of the universe. What Einstein's 160. General Nonsense /161. Beginner's mind realized was that this is so only in our minds. Einstein discovered that certain laws of geometry are valid only in limited regions of space. This makes them useful since our experience physically is limited to very small regions of space, like our solar system. However, as our experience expands, we encounter more and more difficulty in trying to superimpose these rules upon the entire expanse of the universe. Einstein was the first person to see that the geometrical rules which apply to one small part of the universe as seen from a limited perspective, like ours, are not universal. This freed him to behold the universe in a way that no person had seen it before. What he saw is the content of the general theory of relativity. Einstein did not set out to prove anything about the nature of our minds. His interest was in physics. Our new idea, he wrote, is simple to build a physics valid for all coordinate systems. The fact that he did illustrate something of importance about the way that we structure our perceptions is indicative of an inevitable trend toward the merger of physics and psychology. How did Einstein get from a theory of physics to a revolutionary statement of geometry? 3. How did that lead to a significant insight into our mental processes? The answer to these questions is one of the least known, but one of the most important and intriguing intellectual adventures recorded. Einstein started with his special theory of relativity. As successful as it was, Einstein was not satisfied with it because it applied only to coordinate systems moving uniformly. The *U presented high is not that geometry comes from the mind. There are many possible geometries, as Riemann and Lobachevsky showed before Einstein carried, but the actual geometry that we have is determined by the physics. For example, Euclid considered geometry to be closely related to experience. He defined congruence BV moving triangles about M space, and he considered his parallel axiom to be not self-evident, i.e. not a product purely of the mind. The value presented here is that idealizations abstracted from experience, like Euclid in geometry, form a rigid structure of such durability that when subsequent sensory experience contradicts it, we question the validity of the sensor data rather than the validity of the idealized abstractions. Once such a set of idealized abstractions is erected, verified, in the mind, we thereafter superimpose it upon all subsequent actual and projected sensed data, i.e. upon the entire universe as we picture it according to this set of abstractions, whether it fits or not. 162/nonsense. To each other. Is it possible, thought Einstein, to explain the same phenomenon as seen from two different frames of reference, one of them moving uniformly and the other of them moving non-uniformly, in such a way that there is a consistent explanation for the phenomenon in terms of both the uniformly moving frame of reference and the non-uniformly moving frame of reference. In other words, can we describe events which happen in a coordinate system which is moving non-uniformly in terms which are meaningful to an observer, in a coordinate system which is moving uniformly, and the other way round? Can we create one physics that is valid for observers in both frames of reference? Yes, discovered Einstein, it is possible for observers in the two different frames of reference to relate in a manner which is both meaningful in terms of their own state of motion and in terms of the other's state of motion. To illustrate this, he used another famous thought experiment. Imagine an elevator in an extraordinarily tall building. The cable which supports the elevator has snapped, and the elevator is plummeting downward. Inside the elevator are several phys. Ists. They are not aware that the cable has broken, and since there are no windows, they cannot look outside. The question is, what is the appraisal of this situation by the observers on the outside of the elevator, us, and by the observers on the inside of the elevator, the physicists? Since this is an idealized experiment, we can disregard the effects of friction and the resistance of the air. To us, the situation is apparent. The elevator is falling and soon it will strike the earth and all of its inhabitants will be dead. As the elevator falls, it accelerates according to Newton's law of gravity. The motion of the elevator is not uniform, but accelerated because of the gravitational field of the earth. We can predict many things that might happen inside the elevator. For example, if someone inside the elevator dropped a handkerchief, nothing would happen. It would appear to the inside observers to float where it was released because it would be accelerating toward the earth at the same rate as the elevator and the people inside of it. Nothing really would be floating, everything would be falling, but since everything would be falling at the same rate, there would be no change in their relative positions. To a generation of physicists born and brought up inside the elevator, however, things would appear quite differently. General nonsense /163. To them, dropped objects do not fall, they simply hang in midair. If someone gives a floating object a shove, off it goes in a straight line until it hits the side of the elevator. To the observers inside the elevator, there are no forces acting on any objects inside the elevator. In short, the observers inside the elevator would conclude that they are in an inertial coordinate system. 1. The laws of mechanics are perfectly valid. Their experiments always produce results which agree exactly with theoretical predictions. An object at rest remains at rest. An object in motion remains in motion. Moving objects are deflected from their paths only by forces which are proportional to the amount of deflection. For every reaction there is an equal and opposite reaction. If we give a shove to a floating chair, it goes off in one direction, and we go off in the opposite direction with an equal momentum, although with a slower speed because of our greater mass. The inside observers have a consistent explanation for the phenomena inside the elevator. They are in an inertial coordinate system, and they can prove it by the laws of mechanics. The outside observers also have a consistent explanation for the phenomena inside the elevator. The elevator is falling in a gravitational field. Its passengers are unaware of this because, without being able to see outside the elevator, there is no way for them to detect it while they are falling. Their coordinate system is in accelerated motion, even though THEV believe that it is not moving at all. The bridge between these two explanations is gravity. The falling elevator is a pocket edition of an inertial coordinate system. A real inertial coordinate system is not lim. It in space or time. The elevator edition is limited in both. It is limited in space because a moving object inside the elevator will not move in a straight line forever, but only until it reaches one of the walls of the elevator. It is limited in time because sooner or later the elevator and its passengers are going to collide with the Earth, ending their existence abruptly. According to the special theory of relativity, moreover, it is significant that the elevator is limited in size because otherwise it would not appear to its inhabitants as an inertial coordinate system. For example, if the physicists inside the elevator simultaneously drop two baseballs, the baseballs float in the air exactly where they are released, and remain there. This 164 / nonsense to the outside observer is because they are falling parallel to each other. However, if the elevator were the size of Texas, and the baseballs were as far apart when they were dropped as Texas is wide, the baseballs would not fall parallel to each other. They would converge, since each of them would be drawn by gravity to the center of the Earth. The observers inside the elevator would notice that the baseballs, and any other floating objects in the elevator, move toward each other with the passage of time, as though there were a mutual attraction between them. This mutual attraction would appear as a force affecting the objects in the elevator, and the physicists inside hardly would conclude, under those circumstances, that they were in an inertial coordinate system. In short, if it is small enough, a coordinate system falling in a gravitational field is the equivalent of an inertial coordinate system. This is Einstein's principle of equivalence. It is a telling piece of mental dexterity. Anything like an inertial coordinate system that can be wiped out, to Einstein's words, by the assumption of a gravitational field hardly deserves to be called absolute, as in absolute motion and absolute non-motion. While the observers inside the elevator experience a lack of motion and the absence of gravity, the observers outside the elevator see a coordinate system, the elevator accelerating through a gravitational field. Now let us imagine a variation of this situation. Assume that we, the outside observers, are in an inertial coordinate system. We already know what happens in inertial coordinate systems, the same things that happened in the falling elevator. There are no forces, including gravity, to affect us. Therefore, let us assume that we are comfortably floating. Objects at rest remain at rest, objects in motion continue in a straight line forever, and every action produces an equal and opposite reaction. In our inertial coordinate system is an elevator. Someone has attached a rope to the elevator and is pulling it in the direction indicated. Next page. Since this is a thought experiment, it does not matter how this is done. The elevator is being pulled with a constant force, which means that it is in a state of constant acceleration in the direction of the arrow. How will observers outside the elevator and observers inside the elevator appraise this situation? As we float outside the elevator, we experience that our frame of reference is absolutely at rest and that there is no general nonsense /165. Gravity affecting it. We see the elevator being pulled with a constant acceleration by the rope, and so we can predict certain things about it. Everything inside the elevator that is not attached quickly collides with the floor of the elevator. If someone in the elevator drops a handkerchief, the elevator floor rushes up to meet it. If someone in the elevator tries to jump off the floor, rushing upward, is instantly under his feet again. The floor of the elevator continually crashes into anything in its path as it accelerates upward. Inside the elevator, however, the appraisal of the situation is quite different. To a generation of physicists born and brought up inside the elevator, talk of acceleration upward is fantasy. Remember, the elevator has no windows. To them, their coordinate system is quite at rest. Objects fall downward to the floor because of a gravitational field, just as objects on the Earth fall downward to the floor because of a gravitational field. Both the observers inside the elevator and the observers outside the elevator have consistent explanations for the phenomena inside the elevator. We observers outside the elevator explain them by the accelerated motion of the elevator. 166 / The observers inside the elevator explain them by the presence of a gravitational field. There is absolutely no way to determine which of us is right. Wait a minute, we say, suppose that we cut a small hole in one wall of the elevator and shine a light beam through it. If the elevator really were motionless, the light beam would strike the opposite wall of the elevator at a spot exactly opposite the hole. Since we can see that the elevator is accelerating upward, we know that the elevator wall will move upward slightly in the time it takes the light beam to cross the elevator. Therefore the light beam will strike the far wall slightly below the spot just opposite the hole it entered through. In effect, it will seem to curve downward from the point of view of the people inside the elevator instead of traveling in a straight line. This should prove to them that their elevator is in motion. It does not prove anything of the sort, says Jim DeWitt, who of course is inside the elevator. The light beams in this elevator do not travel in straight lines. How could they? One, we are in a gravitational field. Light is energy and energy has mass. Gravity attracts mass, and a light beam traveling through our elevator will be drawn downward by our gravitational field, exactly like a baseball thrown horizontally at the speed of light. There is no way that we can convince DeWitt that his coordinate system is in a state of accelerated motion. Every thing that we can say to prove this to him he dismisses. AC counts for, as a result of his gravitational field, there is absolutely no way of distinguishing between uniform accelerated motion and a constant gravitational field. This is another expression of Einstein's principle of equivalence. In limited areas, gravity is equivalent to acceleration. We already saw that acceleration, falling through a gravitational field, is the equivalent of an inertial coordinate system. Now we say that a gravitational field is equivalent to accelerated motion. At last we are approaching a general theory of relativity, a theory valid for all frames of reference regardless of their states of motion. The bridge which links the explanations of the observers inside of the elevator and the explanations of the observers outside of the elevator is gravity, the clue which indicated to Einstein that gravity was the key to his general theory was as old as physics itself. General nonsense /167. There are two kinds of mass, which means that there are two ways of talking about it. The first is gravitational mass. The gravitational mass of an object, roughly speaking, is the weight of the object as measured on a balance scale, something that weighs 3 times more than another object has 3 times more mass. Gravitational mass is the measure of how much force the gravity of the Earth exerts on an object. Newton's laws describe the effects of this force, which vary with the distance of the mass from the Earth. Although Newton's laws describe the effects of this force, they do not define it. This is the mystery of action at a distance. Page 23. How does the Earth invisibly reach up and pull objects downward? The second type of mass is inertial mass. Inertial mass is the measure of the resistance of an object to acceleration, or deceleration, which is negative acceleration. For example, it takes 3 times more force to move 3 railroad cars from a standstill to 20 miles per hour, positive acceleration, than it takes to move 1 railroad car from a standstill to 20 miles per hour. Page 144. Similarly, once they are moving, it takes 3 times more force to stop 3 cars than it takes to stop the single car. This is because the inertial mass of the 3 railroad cars is 3 times more than the inertial mass of the single railroad car. Inertial mass and gravitational mass are equal. This explains why a feather and a cannonball fall with equal velocity in a vacuum. The cannonball has hundreds of times more gravitational mass than the feather. It weighs more, but it also has hundreds of times more resistance to motion than the feather. Its inertial mass, its attraction to the Earth, is hundreds of times stronger than that of the feather, but then so is its inclination not to move. The result is that it accelerates downward at the same rate as the feather, although it seems that it should fall much faster. The fact that inertial mass and gravitational mass are equal was known 300 years ago, but physicists considered it a coincidence. No significance was attached to it until Einstein published his general theory of relativity. The coincidence of the equivalence of gravitational mass and inertial mass was the clue. 3. To use Einstein's word that led him to the principle of equivalence, which refers via the equivalence of gravitational mass and inertial mass to the equivalence of gravity and acceleration themselves. These are the things that he illustrated with his famous elevator examples. 168 / nonsense. The special theory of relativity deals with unaccelerated uniform motion. If acceleration is neglected, the special theory of relativity applies. However, since gravity and acceleration are equivalent, this is the same as saying that the special theory of relativity is applicable whenever gravity is neglected. If the effects of gravity are to be considered, then we must use the general theory of relativity. In the physical world, the effects of gravity can be neglected in 1. Remote regions of space which are far from any centers of gravity, matter, and 2. In very small regions of space. Why gravity can be ignored in very small regions of space leads to the most psychedelic aspect of all Einstein's theories. Gravity can be ignored in very small regions of space because, if the region is small enough, the mountainous terrain of space time is not noticeable. The nature of the space-time continuum is like that of a hilly countryside. The hills are caused by pieces of matter. Objects. The larger the piece of matter, the more it curves. The space-time continuum. In remote regions of space far from any matter of significant size, the space-time continuum resembles a flat plane. A piece of matter the size of the Earth causes quite a bump in the space-time continuum, and a piece of matter the size of a star causes a relative mountain. As an object travels through the space-time continuum, it takes the easiest path between 2 points. The easiest path between 2 points in the space-time continuum is called a geodesic, geodesic. A geodesic is not always a straight line, owing to the nature of the terrain in which the object finds itself. Suppose that we are in a balloon looking down on a mountain that has a bright beacon on the top of it. The mountain rises gradually out of the plain, and becomes more and more steep as its elevation increases, until, close to the top, it rises most straight up. There are many villages surrounding the The special theory deals with the unaccelerated, uniform motion of coordinate systems. The special theory can be used to describe the accelerated, non-uniform motion of objects as long as the coordinate system from which the object is being observed is itself in uniform motion. Some physicists think that general relativity will be useful on the microscale of high-energy physics, where the effects of gravity usually are ignored. E.g. Strong fluctuations of the gravitational field have been detected at very short distances, 14 cm. General nonsense /169. Mountain, and there are footpaths connecting all of the villages with each other. As the paths approach the mountain, all of them begin to curve in one way or another, to avoid going unnecessarily far up the mountain. Suppose that it is night time and that, looking down, we can see neither the mountain nor the footpaths. All that we can see is the beacon and the torches of the travelers below. As we watch, we notice that the torches deflect from a straight path when they approach the vicinity of the beacon. Some of them curve gently around the beacon in a graceful arc some distance away from it. Others approach the beacon more directly, but the closer they get to it, the more sharply they turn away from it. From this, we probably would deduce that some force emanating from the beacon was repelling all attempts to approach it. For example, we might speculate that the beacon is extremely hot and painful to approach. With the coming of daylight, however, we can see that the beacon is situated on the top of a large mountain and that it has nothing whatever to do with the movement of the torch bearers. They simply followed the easiest paths available to them over the terrain between their points of origin and destination. This masterful analogy was created by Bertrand Russell. In this case, the mountain is the sun, the travelers are the planets, asteroids, comets, and debris from the space program. The footpaths are their orbits, and the coming of daylight is the coming of Einstein's general theory of relativity. The point is that the objects in the solar system move as they do not because of some mysterious force, gravity, exerted upon them at a distance by the sun, but because of the nature of the neighborhood through which they are traveling. Arthur Eddington illustrated this same situation in another way. Suppose, he suggested, that we are in a boat looking down into clear water. We can see the sand on the bottom. and the fish is swimming beneath us. As we watch, we notice that the fish seem to be repelled from a certain point. As they approach it, they swim either to the right or to the left of it, but never over it. From this we probably would deduce that there is a repellent force at that point which keeps the fish away. However, if we should go into the water to get a closer look, we would see that an enormous sunfish has buried him. 170 / self in the sand at that point, creating a sizable mound. As fish swimming along the bottom approach the mound, they follow the easiest path available to them, which is around it. Rather than over it, there is no force causing the fish to avoid that particular spot. If all had been known from the first, that spot was merely the top of a large mound which the fish found easier to swim around than to swim over. The movement of the fish was determined not by a force emanating from the mistinous spot, but by the nature of the neighborhood through which they were passing. Edmonton's sunfish was called Albert. Really, if we could see the geography, the geometry, of the space-time continuum, we would see that, similarly, it, and not forces between objects, is the reason that planets move in the ways that THEV do. It is not possible for us actually to see the geometry of the space-time continuum because it is four-dimensional and our sensory experience is limited to 3 dimensions. For that reason, it is not even possible to picture it. For example, suppose that there existed a world of 2-dimensional people. Such a world would look like a picture on a television or a movie screen. The people and the objects in a 2-dimensional world would have height and width, but not depth. These 2-dimensional figures had a life and an intelligence of their own. Their world would appear quite different to them than our world appears to us, for they could not experience the 3rd dimension. A straight line drawn between 2 of these people would appear to them as a wall. They would be able to walk around either end of it, but they would not be able to step over it, because their physical existence is limited to 2 dimensions. They cannot step off the screen into the 3rd dimension. They would know what a circle is, but there is no way that they could know what a sphere is. In fact, a sphere would appear to them as a circle. If they like to explore, they soon would discover that their world is flat and infinite. If 2 of them went off in opposite directions, they would never meet. They also could create a simple geometry sooner or later. They would forward/e their experiences into abstractions to help them do and build the things that they want to do and build in their physical world. For example, they would discover that whenever 3 straight metal bars form a triangle, the general nonsense /171 angles of the triangle always total 180 degrees. Sooner or later, the more perceptive among them would substitute mental idealizations, straight lines, for the metal bars that would allow them to arrive at the abstract conclusion that a triangle, which by definition is formed by 3 straight lines, always contains 180 degrees. To learn more about triangles, they no longer would need actually to construct them. The geometry that such a 2-dimensional people would create is the same geometry that we studied in school. It is called Euclidean geometry, in honor of the Greek, Euclid, whose thoughts on the subject were so thorough that no one expanded on them for nearly 2,000 years. The content of most high school geometry books is about 2 millennia old. Now let us suppose that someone, unbeknownst to them, transported these two-dimensional people from their flat world onto the surface of an enormously large sphere. This means that instead of being perfectly flat, their physical world now would be somewhat curved at first. No one would notice the difference, however, if their technology improved enough to allow them to begin to travel and to communicate over great distances. These people eventually would make a remarkable discovery. They would discover that their geometry could not be verified in their physical world. For example, they would discover that if they surveyed a large enough triangle and measured the angles that form it, it would have more than 180 degrees. This is a simple phenomenon for us to picture. Imagine a triangle drawn on a globe. The apex, top, of the triangle is at the North Pole. The two lines intersecting there form a right angle. The equator is the base of the triangle. Look what happens. Both sides of the triangle, upon intersecting the equator, also form right angles. According to Euclidean geometry, a triangle contains only two right angles, 180 degrees. Yet this triangle contains three right angles, 270 degrees. Remember that in our example, the two-dimensional people actually have surveyed a triangle on what they presumed was their flat world, measured the angles, and come up with 270 degrees. What a confusion! When the dust settles, they would realize that there are only two possible explanations. The first possible explanation is that the straight lines used to construct the triangle, like light beams, were not actually straight, although they seemed to be straight. This could AC 172 nonsense count for the excessive number of degrees in the triangle. However, if this is the explanation that they choose to adopt, then they must create a force responsible for somehow distorting the straight lines, like gravity. The second possible explanation is that their abstract geometry does not apply to the real world. This is another way of saying that, impossible as it sounds, their universe is not Euclidean. The idea that their physical reality is not Euclidean probably would sound so fantastic to them, especially if they had had no reason to question the reality of Euclidean geometry for 2,000 years, that they probably would choose to look for forces responsible for distorting their straight lines. Asterisk. The problem is that, having chosen this course, they would be obligated to create a responsible force every time that their physical world failed to validate Euclidean geometry. Eventually the structure of these necessary forces would become so complex that it would be much simpler to forget them altogether and admit that their physical world does not follow the logically irrefutable rules of Euclidean geometry. Our situation is parallel to that of the two-dimensional people who cannot perceive, but who can deduce that they are living in a three-dimensional world. We are a three-dimensional people who cannot perceive, but who can deduce that we are living in a four-dimensional universe. For 2,000 years we have assumed that the entire physical universe, like the geometry that the ancient Greeks created from their experience with this part of it, was Euclidean. That the geometry of Euclid is universally valid means that it can be verified anywhere in the physical world. That assumption was wrong. Einstein was the first person to see that the universe is not bound by the rules of Euclidean geometry, even though our minds tenaciously cling to the idea that it is. Although we cannot perceive the four-dimensional space time continuum directly, we can deduce from what we already know of the special theory of relativity that our universe is not Euclidean. Here is another of Einstein's thought experiments. Imagine two concentric circles, one with a small radius and Eddington expressed this concept most concisely. A field of E represents the discrepancy between the natural geometry of a coordinate system and the abstract geometry arbitrarily ascribed to it. Arthur Eddington, The Mathematical Theory of Relativity, Cambridge, England, Cambridge University Press. 1923, pp. 37-38. Italics in the original. General Nonsense /173. One with a very large radius. Both of them revolve around a common center as shown. Imagine also that we, the observers, are watching these revolving circles from an inertial coordinate system. Being in an inertial coordinate system simply means that our frame of reference is at rest relative to everything, including the revolving circles. Drawn over the revolving circles are two identical concentric circles which are in our coordinate system. They are not revolving. They are the same size as the revolving circles and have the same common center, but they remain motionless, while we and our non-revolving circles are motionless. We are in communication with an observer who is on the revolving circles. He actually is going around with them. According to Euclidean geometry, the ratio of the radius to the circumference of all circles is the same. If we measure the radius and the circumference of the small circle, for example, the ratio of these two measurements will be the same as the ratio of the radius to the circumference of the large circle. The object of this thought experiment is to determine whether this is true or not for both the observers on the stationary circles, us, and the observer on the revolving circles. If the geometry of Euclid is valid throughout the physical universe, as it should be, we should discover that the ratio between the 174/nonsense radius and the circumference of all the circles involved is identical. Both we and the observer on the revolving circles will use the same ruler to do our measuring. The same ruler means that either we actually hand him the same ruler that we have used, or that we use rulers that have the same length when at rest in the same coordinate system. We go first. Using our ruler, we measure the radius of our small circle, and then we measure the circumference of our small circle. Then we note the ratio between them. The next step is to measure the radius of our large circle and then the circumference of our large circle. Then we note the ratio between them. Yes, it is the same ratio that we found between the radius and the circumference of our small circle. We have proved that Euclidean geometry is valid in our coordinate system, which is an inertial coordinate system. Now we hand the ruler to the observer on the revolving circles as he passes by us. Using this ruler he first measures the radius of his small circle and finds that it is the same as ours, since our circles are drawn directly over his circles. Next he measures the circumference of his small circle. Remember that motion causes rulers to contract in the direction that they are moving. However, since the radius of the small circle is so short, the velocity of the ruler when it is placed on the circumference of the small circle is not fast enough to make the effect of relativistic contraction noticeable. Therefore, the observer on the revolving circles measures the circumference of his small circle and finds it to be the same as the circumference of our small circle. Naturally, the ratio between them also is the same. So far so good. The ratios between the radius and the circumference of three circles have been determined: our small circle, our large circle, and his small circle, and they all are identical. This is exactly what should happen according to high school geometry books across the country. Only one more circle to go. The observer on the revolving circles measures the radius of his large circle and finds it to be the same length as the radius of our large circle. Now he comes to the last measurement, the circumference of his large circle. However, as soon as he puts his ruler into position to make a measurement on the circumference of the large revolving circle, his ruler contracts, because the radius of his large circle is much larger than general nonsense /175. The radius of his small circle, the velocity of the circumference of the large revolving circle, is considerably faster than the velocity of the circumference of the small revolving circle. Since the ruler must be aligned in the direction that the circumference is moving, it becomes shorter. When the revolving observer uses this ruler to measure the circumference of the large revolving circle, he finds that it is larger than the circumference of our large circle. This is because his ruler is shorter. Contraction also affected his ruler when he measured the radius of his large circle, but since it then was placed perpendicular to the direction of motion, it became skinnier, not shorter. This means that the ratio of the radius to the circumference of the small revolving circle is not the same as the ratio of the radius to the circumference of the large revolving circle. AC. According to Euclidean geometry, this is not possible, but there it is. If we want to be old-fashioned about it, before Einstein, we can say that this situation is nothing unusual. By definition, the laws of mechanics and the geometry of Euclid are valid only in inertial systems. That is what makes them inertial systems. We simply don't consider coordinate systems which are not inertial. This was really the position of physicists before Albert Einstein. This is exactly what seemed wrong to Einstein. His idea was to create a physics valid for all coordinate systems. Since the universe abounds with the non-inertial as well as the inertia kind. If we are to create such a universally valid physics, a general physics, then we must treat both the observers in the stationary, inertial system and the observer on the revolving circles, a non-inertial system, with equal seriousness. The sun on the revolving circles has as much right to relate the physical world to his frame of reference as we have to relate it to ours. True, the laws of mechanics as well as the geometry of Euclid are not valid in his frame of reference, but every deviation from them can be explained in terms of a gravitational field which affects his frame of reference. This is what Einstein's theory allows us to do. It allows us to express the laws of physics in such a way that they are independent of specific space-time coordinates. Space and time coordinates, measurements, vary from one frame of Reference to another, depending upon the state of motion of 176/nonsense. The frame of reference. The general theory of relativity allows us to universalize the laws of physics and to apply them to all frames of reference. Wait a minute, we say, how can anyone measure distance or navigate in a coordinate system like the one on the revolving circles? The length of a ruler varies from place to place in such a system. The farther we go from the center, the faster the velocity of the ruler, and the more it contracts. This doesn't happen in an inertial coordinate system, which, in effect, is a system that is at rest, because there is no change of velocity. Throughout an inertial coordinate system, rulers do not change length. This allows us to organize inertial systems like a city, block by block. Since rulers do not change length in inertial systems, all the blocks that are laid out with the same ruler will be the same length. No matter where we travel, we know that 10 blocks is twice the distance of 5 blocks. In a non-inertial system, the velocity of the system varies from place to place. This means that the length of a ruler varies from place to place. If we used the same ruler to lay out all the city blocks in a non-inertial coordinate system, some of them would be larger than others depending upon where they were located. What is wrong with that, asks Jim DeWitt, as long as we still can determine our position in the coordinate system. Imagine a sheet of India rubber on which we have drawn a grid so that it looks like a piece of graph paper. First drawing. Opposite page. This is a coordinate system. Assuming that we are at the lower left corner, we can start anywhere. Let us say that a party Saturday night is being held at the intersection marked party. To get there we have to go 2 squares to the right and 2 squares up. Now suppose that we stretch the sheet of rubber so that it looks like the second drawing. The same directions, 2 squares right and 2 squares up, still bring us to the party. The only difference is that unless we are familiar with this part of the coordinate system, we cannot calculate the distance that we have to travel as easily as we could if all of the squares were the same size. According to the general theory of relativity, gravity, which is the equivalent of acceleration, is what distorts the space-time continuum in a manner analogous to our stretching the general nonsense /177 party sheet of rubber, where the effects of gravity can be neglected. The space-time continuum is like the sheet of rubber before we stretched it. All of the lines are straight lines and all of the clocks are synchronized. In other words, the undistorted sheet of rubber is analogous to the space-time continuum of an inertial coordinate system, and the special theory of relativity applies. However, in the universe at large, gravity cannot be neglected. Wherever there is a piece of matter, it warps the space-time continuum. The larger the piece of matter, the more pronounced the warp. In the example of the revolving circles, the variation of velocity in different parts of the coordinate system caused the ruler to change size. With that in mind, remember that acceleration, change in velocity, is the equivalent of gravity. Therefore, changes in the strength of a gravitational field will produce the same contractions of the ruler as changes in velocity. Acceleration and gravity are two ways of saying the same thing. That means that if a ruler is subjected to gravitational fields of different strength, it changes length. 178 nonsense. Of course, it is impossible to travel through our solar system, much less our galaxy, without encountering gravitational fields of varying intensity, which would cause any maps that we somehow could produce to look distorted like the stretched piece of India rubber. The terrain of the space-time continuum in which our Earth moves is like a hill countryside with a mountain, the sun, dominating the geography. According to Newton, the Earth wants to continue forever in a straight line, but forever is deflected from its inclination by the gravitational force of the Sun. A balance of the two keeps the Earth in orbit around the Sun according to Einstein. The Earth's orbit is simple, the easiest path for the Earth to take as it moves through the space-time continuum, warped as it is in this neighborhood by the Sun. Imagine how complex is the geography of the space-time continuum, which is our universe with its solar systems, star systems, galaxies, and galax clusters, each of them causing major and minor bumps, curves, hills, valleys, and mountains in the four-dimensional space-time continuum. Would it be possible to navigate under such circumstances? Yes, although it is a crude example, sailors navigate under somewhat analogous circumstances. We cover the Earth with squares which are formed by lines of latitude and longitude. The size of these squares varies depending upon where they are located. The closer they are to the equator, the larger they are. If this is unclear, look at a globe. Nonetheless, we still can locate physical points on the surface of the Earth by designating the intersection of a line of latitude and a line of longitude. Knowing the number of squares between us and where we want to sail does not give us the distance to our destination, because the squares may vary in size. However, if we know the nature of our terrain, a globe, we can calculate distances on it, using spherical trigonometry. Similarly, once we know the properties of an area of the space-time continuum, by exploring it, we can determine not only the position of, but also the distance, interval, between two events in the space-time continuum. The mathematical structure of the general theory of relativity, which Einstein created over a period of 10 years, permits us to do just that. This distance of course is invariant, i.e. the same for all coordinate stems. Page 152. The invariance is the absolute objective aspect of Einstein's theory that complements the subjective arbitrary choice of coordinate system. General nonsense /179. The equations of the general theory of relativity are structural formulas. They describe the structure of changing gravitational fields. Newton's formula describes a situation between two objects at a given time. Einstein's formulas relate a situation here and now to a situation in the immediate vicinity a little later, by feeding the results of actual observations into these equations. They give us a picture of the space-time continuum in the neighborhood of our observation. In other words, they reveal the geometry of space-time in that area. Once we know that our situation is roughly analogous to that of a sailor who knows that the Earth is round and also knows Sohn trigonometry T. We have said, up to now, that matter distorts, or causes a curvature of the space-time continuum in its vicinity according to Einstein's ultimate vision, which he never proved. Demonstrated mathematically, a piece of matter is a curvature of the space-time continuum. One, in other words. According to Einstein's ultimate vision, there are no such things as gravitational fields and masses, they are only mental creations. No such things exist in the real world. There is no such thing as gravity. Gravity is the equivalent of acceleration, which is motion. There is no such thing as matter. Matter is a curvature of the space-time continuum. There is not even such a thing as energy. Energy equals mass, and mass is space-time curvature. What we considered to be a planet with its own gravitational field moving around the Sun in an orbit created by the gravitational attraction force of the Sun is actually a pronounced curvature of the space-time continuum, finding its easiest path through the space-time continuum in the vicinity of a very pronounced curvature of the space-time continuum. The P is nothing but space-time and motion, and they, in effect, are the same thing. Here is an exquisite presentation, in completely Western terms, of the most fundamental aspect of Taoist and Buddhist philosophies. Physics is the study of physical reality. If a theory does not relate to the physical world, it may be pure mathematics. T1 height space-time continuum is not only curved, it also has topologies, properties, i.e. it can be connected in crazy ways, e.g. like a donut carrot. It also can twist, i.e. torsion, carrot, carrot. 180 / nonsense. Poetry, or blank verse, but it is not physics. The question is, does Einstein's fantastic theory really work? The answer is a slightly tentative, but generally accepted yes. Most physicists agree that the general theory of relativity is a valid way of viewing large-scale phenomena, and at the same time, most physicists still are eager to see more evidence to confirm, or challenge, this position. Since the general theory of relativity deals with vast expanses of the universe, its proof of usefulness, not of truth, the which is still unopenable, cannot come from observations of phenomena limited to the Earth. For this reason, its verifications come from astronomy. Thus far, the general theory of relativity has been verified in 4 ways. The first 3 ways are straightforward and convincing. The last way, if early observations are correct, may be more fantastic than the theory itself. The first verification of the general theory of relativity came as an unexpected benefit to astronomers. Newton's law of gravity purported to describe the orbits of the planets around the Sun. And it did. All of them except Mercury. Mercury orbits the Sun in such a way that some parts of its orbit bring it closer to the Sun than others. The part of Mercury's orbit closest to the Sun is called its perihelion. The first verification of Einstein's general theory of relativity turned out to be the long-sought explanation of the problem of Mercury's perihelion. The problem with Mercury's perihelion, in fact, with Mercury's entire orbit, is that it moves instead of continuously retracing its path around the Sun relative to a coordinate system attached to the Sun. Mercury's orbit itself revolves around the Sun. The rate of revolution is extremely slow. It completes 1 revolution around the Sun every 3 million years. This still was enough to push forward astronomers prior to Einstein. This precession in Mercury's orbit had been attributed to an undiscovered planet in our solar system by the time Einstein published his general theory of relativity. The search For this mysterious planet was well underway. Einstein created his general theory of relativity without special attention to the perihelion of Merkurov. However, when the general theory of relativity was applied to this problem, it showed that Mercury moves precisely as Mercury has to move through the space-time continuum in that vicinity of the Sun. The other planets do not move significantly in this way. B. General nonsense /181. Cause they are farther away from the Sun's gravity store 1. For the general theory. The second verification of the genera, theory of relativity, was the fulfillment of a prediction specifically made by Einstein. Einstein predicted that light beams are bent by gravitational fields. He also predicted exactly how much they are bent, and he suggested an experiment to test this prediction. Einstein suggested that astronomers measure the deflection of starlight by the gravitational field of the Sun. According to Einstein, the presence of the Sun between a group of visible stars and the Earth will cause an apparent change in the position of the stars because light coming from them will be bent by the gravitational field of the Sun. In order to perform this experiment, it is necessary to photograph a group of stars at night, noting their positions relative to each other and other stars on their periphery, and then to photograph the same group during the day when the Sun is between them and us. Of course, stars on Earth can be photo 182/nonsense graphed in the daytime during a total eclipse of the Sun by the Moon. Astronomers consulted their star charts and discovered that the 29th of May is the ideal day for such an undertaking. This is because the Sun, in its apparent journey across a varied stellar background, is in front of an exceptionally rich grouping of bright stars on that date. By incredible coincidence, a total eclipse of the Sun occurred on the 29th of May, 1919, only 4 years after the general theory was published. Preparations were made to use this event to test Einstein's new theory. Light signals from a star are bent in the neighborhood of the Sun. Because we assume that starlight travels in a straight line, we assume that the star is in a position other than it actually is. Although light was supposed to travel in a straight line in a vacuum, a certain amount of bending already was theorized before Einstein's general theory of relativity. Newton's law of gravity was used to calculate this bending, even though it could not explain it. Einstein's theory predicted roughly twice the deflection that Newton's law predicted, and, in addition, it supplied an explanation for it. Physicists and astronomers alike eagerly awaited the outcome of this confrontation between the new theory and the old. The 1919 eclipse was photographed by 2 different expeditions sent to 2 different parts of the world. These expeditions also took photographs of the same stellar background at times when the Sun was not in the area. The results of both expeditions vindicated Einstein's calculations, not Newton's. Since 1919, the same verdict has been reached again and again during other eclipses. All of them confirm Einstein's predictions. Score 2 for the general theory. The third verification of the general theory of relativity is called gravitational redshift. Remember that gravity, because general nonsense /183. It is the equivalent of acceleration, not only causes rulers to contract, but it also causes clocks to run more slowly. A clock is anything that repeats itself periodically. An atom is a type of clock. It vibrates at a certain frequency. When a substance, like sodium, is made to glow, the wavelength of the light that it emits can be measured accurately. This wavelength tells us exactly the frequency of the vibrations of the atoms that comprise the substance. If the frequency should vary, the wavelength also will vary. If we want to compare the rhythm of a clock here on the Earth with the rhythm of a clock that is influenced by an intense gravitational field, like that of the Sun, we do not need to send a clock to the surface of the Sun. The clocks already are in place. Einstein predicted that any periodic process that takes place in an atom on the Sun, where the gravity is very intense, must take place at a slightly slower rate than it does here on the Earth. To test this prediction, all we need do is compare the wavelength of the radiation of a given element as it is found in sunlight and as it is found here on Earth in the laboratory. This has been done many times. In each case, the wavelength measured from the sunlight was found to be longer than its laboratory counterpart. A longer wavelength means a lower, slower frequency. Sodium atoms, for example, vibrate more slowly under the influence of the Sun's strong gravitational field than they do on the Earth. So do all the atoms. This phenomenon is called gravitational redshift because the wavelengths involved appear to be shifted slightly toward the red end of the visible light spectrum where the wavelengths are the longest. Score 3 for the general theory. Mercury's moving perihelion, starlight deflection, and gravitational redshift are all observable phenomena. Now we come to an area where theory is still predominant and observation is minimal. Nonetheless, it is an area that is by far the most exciting and perhaps the most stimulating in the entire history of science. The fourth verification of the general theory of relativity appears to be the phenomenon of the black hole. In 1958, David Finkelstein published a paper in which he theorized, on the basis of Einstein's general theory of relativity, a phenomenon that he called a one-way membrane for Finkelstein showed that under certain conditions involving an extremely dense gravitational field, an invisible threshold can 184/nonsense occur into which light and physical objects can enter, but from which they never again can escape. The following year, a young graduate student at the University of London heard Finkelstein, who was speaking there as a guest lecturer, explain his one-way membrane. The idea caught his attention and then his imagination. The young student was Roger Penrose. Expanding on Finkelstein's discovery, he developed it into the modern theory of the black hole. A black hole is an area of space which appears absolutely black because the gravitation there is so intense that not even light can escape into the surrounding areas. Gravitation is negligible on the laboratory level, but quite important when bodies of large mass are concerned. Therefore, the exploration of black holes naturally became a joint venture of physicists and astronomers. Astronomers speculated that a black hole may be one of several possible products of stellar evolution. Stars do not burn indefinitely. They evolve through a life cycle which begins with hydrogen gas and sometimes ends with a very dense, burnt out, rotating mass. The exact end product of this process depends upon the size of the star undergoing it. According to one theory, stars which are about 3 times the size of our Sun or larger end up as black holes. The remains of such stars are unimaginably dense. They may be only a few miles in diameter and yet contain the entire mass of a star, 3 times larger than the Sun. Such a dense mass produces a gravitational field strong enough to pull everything in its vicinity into it, while at the same time allowing nothing, not even light, to escape from it. Surrounding this remainder of a star is an even horizon. An even horizon is created by the enormous gravitational field of the burnt-out star. It functions precisely like Finkel. * this pi Newtonia modern point of view, i.e., relativity theory of this modern formulation triggered phenomenon was theorized by Pierre Simon Laplace in 1795 using physics. Finkelstein was the first physicist to formulate it from the V and S psi singularity R Penrose and S\V Hawking plus carried to a first approximation. Physicists currently theorize that black holes actually shine due to photons and other particles quantum tunneling out of the one-way membranes. Theories on the black hole. First modern paper on black holes was done by J.R. Oppenheimer in 1939. The current theories of the black hole, i.e., black hole S which are on space-time, were developed independent, b. General Nonsense /185. Stein's one-way membrane. Anything within the gravitational field of this mass quickly is pulled toward it, and once past the event horizon, never can return. It is the event horizon which constitutes the essential feature of the black hole. What happens to an object that passes through an event horizon is even more fantastic than the wildest, currently, science fiction. If the black hole is not rotating, the object will be pulled directly to the center of the black hole TJ, a point called the singularity. There it literally will be squeezed out of existence. Or as physicists say, to zero volume. At the black hole singularity, all of the laws of physics break down completely, and even space and time disappear. It is speculated that everything which is sucked into a black hole is spilled out again on the other side being another universe. If the black hole is rotating, an object that is sucked into the event horizon could miss the black hole singularity, which is shaped like a ring in a rotating black hole, and emerge into another time and another place in this universe, through wormholes, or into another universe, through Einstein-Rosen bridges. In this way, rotating black holes may be the ultimate time machines. Although black holes are almost invisible, we can search for observable phenomena that may be characteristic of them. The first of these is a large amount of electromagnetic radiation. A black hole continuously attracts hydrogen atoms, cosmic particles, and everything else to it. As these particles and objects are drawn to the black hole, they steadily accelerate through its gravitational field until they approach the velocity of light itself. This causes tremendous amounts of electromagnetic radiation. any accelerating charged particle creates electromagnetic radiation. The second observable characteristic of an invisible black hole is its effect on a nearby visible star. If a visible star can be found which moves as though it were revolving around an invisible star, i.e., as though it were half of a binary star system, we might speculate that it actually is revolving around an invisible star, and that its invisible partner is a black hole. The search for black holes consequently became the search for these two phenomena. In 1970, the satellite Uhuru located both of them in one area. It pinpointed a high-energy X-ray source in the constellation Cygnus which emits a million times more energy than the Sun. This high-energy source of electromagnetic radiation, which came to be known as 186/nonsense. Cygnus X1 is very close to a visible blue hot supergiant star. Scientists now believe that this blue supergiant forms a binary system with the black hole Cygnus X1. As the visible star and the invisible black hole orbit each other, the blue supergiant literally is being sucked into the black hole. As material is torn away from its surface, it plunges into the black hole at tremendous speed, emitting X-rays. Incredible as Cygnus X1 is, more than 100 similar objects have been detected within our own Milky Way galaxy since its discovery. Although black holes stretch our imagination to the limit, the evidence is mounting that they actually do exist. For example, if black holes are as we have speculated them to be, whatever disappears into them reappears somewhere. Is it possible, therefore, that there are black holes in other universes which are sucking matter from those universes into our universe? This is a seriously considered possibility. There are objects in our universe that appear to be the reverse of black holes. They are called white holes. Of course, these objects are quasi-stellar radio sources, or quasars for short. Quasars are extraordinarily intense energy sources. Most of them are only several times the diameter of our solar system. Yet they emit more energy than an entire galaxy of over 150 billion stars. Some astronomers believe that quasars are the most distant objects ever detected, yet their incredible brightness allows us to see them clearly. The relationship between black holes and quasars is purely speculation, but the speculation is mind-boggling. For example, some physicists speculate that black holes swallow up matter from one universe and pump it either into another universe or into another part and time of the same universe. The output side of a black hole, according to this hypothesis, is a quasar. If this speculation is correct, then our universe is being sucked into its many black holes, only to reappear in other universes, while other universes are being pumped into our own universe, which is being sucked through black holes and into other universes again. The process goes on and on, feeding on itself, another endless Bendless dance. One of the most profound byproducts of the general theory of relativity is the discovery that gravitational force, which we had so long taken to be a real and independently existing general nonsense /187 thing, is actually our mental creation. There is no such thing in the real world. The planets do not orbit the Sun because the Sun exerts an invisible gravitational force on them. They follow the paths that they do because those paths are the easiest ways for them to traverse the terrain of the space-time continuum in which they find themselves. The same is true for nonsense. It is a mental creation. There is no such thing in the real world. From one frame of reference, black holes and event horizons make sense. From another frame of reference, absolute non-motion makes sense. Neither is nonsense except as seen from another point of view. We call something nonsense if it does not agree with the rational edifices that we carefully have constructed. However, there is nothing intrinsically valuable about these edifices. In fact, themselves often are replaced by more useful ones. When that happens, what was nonsensical from an old frame of reference can make sense from a new frame of reference, and the other way round. Like measurements of space and time, the concept of nonsense, itself a type of measurement, is relative, and we always can be sure when we use it that from some frame of reference it applies to us. Part 1. I clutch my ideas. Chapter 1. The particle zoo. The fourth translation of Wu Li is I clutch my ideas. This is appropriate to a book on physics, since the history of science in general often has been the story of scientists vigorously fighting an onslaught of new ideas. This is because it is difficult to relinquish the sense of security that comes from a long and rewarding acquaintance with a particular world view. The value of a physical theory depends upon its usefulness. In this sense, the history of physical theories might be said to resemble the history of individual personality traits. Most of us respond to our environment with a collection of automatic responses that once brought desirable results, usually in childhood. Unfortunately, if the environment that produced these responses changes, we grow up, and the responses themselves do not adapt, they become counterproductive. Showing anger, becoming depressed, flattering, crying, and bullying behavior are response patterns appropriate to times often long past. These patterns change only when we are forced to realize that they are no longer productive. Even then, change is often painful and slow. The same is true of scientific theories. Not one person, except Copernicus, wanted to accept the Copernican idea that the Earth revolves around the Sun. Goethe wrote about the Copernican revolution. Perhaps a greater demand has never been laid upon mankind, for by this admission, that the Earth is not the center of the universe, how much else did not collapse in dust and smoke, a second paradise, a world of innocence, poetry, and piety, the witness of the senses, the convict. 191. 192 / I clutch my ideas. Tions of a poetic and religious faith. No wonder that men had no stomach for all this, that they ranged themselves in every way against such a doctrine. Not one physicist, not even Planck himself, wanted to accept the implications of Planck's discovery, for to do so threatened a scientific structure, Newtonian physics, over 300 years old. Heisenberg wrote about the quantum revolution. When new groups of phenomena compel changes in the pattern of thought, even the most eminent of physicists find immense difficulties. For the demand for change in the thought pattern may engender the feeling that the ground is to be pulled from under one's feet. I believe that the difficulties at this point can hardly be overestimated. Once one has experienced the desperation with which clever and conciliatory men of science react to the demand for a change in the thought pattern. One can only be amazed that such revolutions in science have actually been possible at all. 2. Scientific revolutions are forced upon us by the discovery of phenomena that are not comprehensible in terms of the old theories. Old theories die hard. Much more is at stake than the theories themselves. To give up our privileged position at the center of the universe, as Copernicus asked, was an enormous psychological task. To accept that nature is fundamentally irrational, governed by chance, which is the essential statement of quantum mechanics, is a powerful blow to the intellect. Nonetheless, as new theories demonstrate superior utility, their adversaries, however reluctantly, have little choice but to accept them. In so doing, they also must grant a measure of recognition to the world views that accompany them. Today, particle accelerators, bubble chambers and computer printouts are giving birth to another world view. This world view is as different from the world view at the beginning of this century as the Copernican world view was from its predecessors. It calls upon us to relinquish many of our closely clutched ideas. In this world view there is no substance. The most common question that we can ask about an object is, what is it made of? That question, however, what is it made of, is based upon an artificial mental structure that is much like a hall of mirrors. If we stand directly between the particles U/193 mirrors and look into one, we see our reflection, and, just behind ourselves, we see a crowd of us, each looking at the back of the head in front of it, stretching backward as far as we can see. These reflections, all of them, are illusions. The only real thing in the whole setting is us, we. This situation is very similar to what happens whenever we ask of something, what is it made of? The answer to such a question is always another something to which we can apply the same question. Suppose, for example, that we ask of an ordinary toothpick, what is it made of? The answer, of course, is wood. However, the question itself has taken us into a hall of mirrors. Because now we can ask about the wood, what is it made of? Closer examination reveals that wood is made of fibers. What the fibers are made of is another question, and so on. Like a pair of parallel mirrors, reflecting reflections, gives the illusion of an unending progression to nowhere. The idea that a thing can be different from what it is made of creates an infinite progression of answers, leaving us forever frustrated in an unending search. No matter what something, anything, is made of, we have created an illusion which forces us to ask, yes, but what is that made of? Physicists are people who have pursued tenaciously this endless series of questions. What they have found is startling. Wood fibers, to continue the example, are actually patterns of cells. Cells, under magnification, are revealed to be patterns of molecules. Molecules, under higher magnification, are discovered to be patterns of atoms, and, lastly, atoms have turned out to be patterns of subatomic particles. In other words, matter is actually a series of patterns out of focus. The search for the ultimate stuff of the universe ends with the discovery that there isn't any. If there is any ultimate stuff of the universe, it is pure energy, but subatomic particles are not made of energy. They are energy. This is what Einstein theorized in 1905. Subatomic interactions, therefore, are interactions of energy with energy. At the subatomic level there is no longer a clear distinction between what is and what happens, between the actor and the action. At the subatomic level the dancer and the dance are one. According to particle physics, the world is fundamentally dancing energy, energy that is everywhere and incessantly. 194 / I clutch my ideas. Assuming first this form and then that what we have been calling matter, particles, constant K is being created annihilated and created again. This happens as particles interact, and it also happens literally out of nowhere. Where there was nothing there suddenly is something. And then the something is gone again, often changing into something else before vanishing. In particle physics there is no distinction between empty as in empty space and not empty / or between something and not something. The world of particle physics is a world of sparkling energy, forever dank mg with itself in the form of its particles as they twinkle in and out of existence, collide, transmute and disappear again. The world view of particle physics is a picture of chaos. Beneath order at the fundamental level is a confusion of continual creation, annihilation and transformation. Above this confusion, limiting the forms that it can take, are a set of conservation laws. Page 156. They do not specify what must happen as ordinary laws of physics do, rather they specify what cannot happen. They are permissive laws. At the subatomic level, absolutely everything that is not forbidden by the conservation laws actually happens. Quantum theory describes the probabilities of the possibilities permitted by the conservation laws. As Jack Sarfati wrote, particles no longer move stiffly and formally, if not majestically in predetermined paths, rather it is Marx Brothers hypocmetic pandemonium. Charlie Chaplin. Slapstick helter-skelter. Now you see it, now thou don't. In fact it is not even clear what it is that has a path. It's psychedelic confusion, until one sees the subtle order. 3. The old world view was a picture of order beneath chaos. It assumed that beneath the prolific confusion of detail that constitutes our daily experience he systematic and rational laws, which relate them one and all. This was Newton's great insight. The same laws which govern falling apples govern the motion of planets. There is still of course much truth in this, but the world view of particle physics is essentially the opposite. The world view of particle physics is that of a world without stuff, where what is equals what happens and where an unending tumultuous dance of creation, annihilation and transformation. The particle zoo /195 runs unabated within a framework of conservation laws and probability. High-energy particle physics is study of subatomic particles. It usually is shortened to particle physics. Quantum theory and relativity are the theoretical tools of particle phys. ICS. The hardware of particle physics is housed in unimaginably expensive facilities which couple particle accelerators and computers. The original purpose of particle physics was to discover the ultimate building blocks of the universe. This was to be AC const BV, breaking matter into smaller and smaller pieces, eventually arriving at the smallest pieces possible. The experimental results of particle physics, however, have not been so simple today most particle physicists are engaged in making sense out of their copious findings. In principle particle physics hardly could be simpler. Phys. Physicists send subatomic particles smashing into each other as hard as they can. They use one particle to shatter another particle so that they can see what the remains are made of. The particle that does the smashing is called the projectile, and the particle that gets smashed is called the target. The most advanced and expensive particle accelerators send both the projectile and the target particles flying toward a common collision point. The collision point usually is located inside a device called a bubble chamber. As charged particles move through a bubble chamber, they leave trails similar to the vapor trails that jet liners leave in the atmosphere. The bubble chamber is located inside a magnetic field. This causes particles with a positive charge to curve in one direction and particles with a negative charge to curve in the opposite direction. The mass of the particle can be determined by the tightness of the curve that the particle makes. Lighter particles curve more than heavier particles with the same velocity and charge. A computer triggered camera makes a photograph every time a particle enters the bubble chamber. The present state of High-Incog theory is similar to Ptolemaic astronomy. Before its collapse under the pressure of the new Uonican worldview, the discovery of new particles and new quantum numbers, e.g. charm, to be discussed later, is analogous to the addition of epicycles piled on an already unequaled theoretical structure. 196 / I clutch my ideas. This elaborate arrangement is necessary because most particles live much less than a millionth of a second and are too small to be observed directly. In general, everything a particle physicist knows about subatomic particles, he deduces from his theories and from photographs of the tracks that particles leave in a bubble chamber. Bubble chamber photographs, thousands and thousands of them, show clearly the frustrating situation which early particle physicists encountered in their search for elementary particles. When the projectile strikes the target, both particles are destroyed at the point of impact. In their place, however, are created new particles, all of which are as elementary as the original particles and often as massive as the original particles. The same. The schematic diagram above shows a typical particle interaction. A particle called a negative pi meson, it, collides with a proton, p. Both the pi meson and the proton are destroyed, and in their place are created two new particles, a neutral k meson, k degree, and a lambda particle, a. Both of these particles decay spontaneously, no collision necessary, into two additional particles, leaving four new particles. Of these four particles, two of them are the same particles that we started with. It is as though, wrote Finkelstein, we fling two clocks together. They shatter, and out of them come flying not gears and springs, but more clocks, some of them as large as the originals. How can this happen? The answer is partly given by the dark adapted eye can detect single photons. All of the other subatomic particles must be detected indirectly. In addition to bubble chamber physics there is emulsion, photographic plate physics, counter physics, etc. However, the bubble chamber is probably the most commonly used detection device in particle physics. The particles UI 197. Einstein's special theory of relativity. The new particles are created from the kinetic energy, energy of motion, of the projectile particle in addition to the mass of the projectile particle and the mass of the target particle. The faster the projectile particle is traveling, the more kinetic energy is able to create new particles at the point of impact. For this reason, governments have spent more and more money to construct larger and larger particle accelerators which can push projectile particles to higher and higher velocities. If both the projectile particle and the target particle are accelerated to the point of impact, so much the more kinetic energy is able to create new particles to study. Every subatomic interaction consists of the annihilation of the original particles and the creation of new subatomic particles. The subatomic world is a continual dance of creation and annihilation, of mass changing to energy and energy chang into mass. Transient forms sparkle in and out of existence, creating a never-ending, forever newly created reality. Mystics from both the East and the West who claim to have beheld the face of God speak in terms so similar to these, that any psychologist who professes an interest in altered states of awareness scarcely can ignore this obvious bridge between the disciplines of physics and psychology. The first question of particle physics is, what collides? According to quantum mechanics, a subatomic particle is not a particle like a particle of dust. Rather, subatomic particles are tendencies to exist, page 32, and correlations between macroscopic observables, page 70. They have no objective existence. That means that we cannot assume, if we are to use quantum theory, that particles have an existence apart from their interactions with a measuring device, page 95. As Heisenberg wrote, in the light of the quantum theory, elementary particles are no longer real in the same sense as objects of daily life, trees or stones. 4. The mass/energy dualism of our ordinary conceptualizations does not exist in the formalism of relativity or quantum theory. According to Einstein's E equals m², mass does not change into energy or vice versa, energy is mass. Wherever energy, E, is present, mass, m, is present and the amount of mass, m, is given by E equals m². The total amount of energy, E, is conserved, and hence the total amount of mass, m, also is conserved. This mass, m, is defined by the fact that it is a source of the gravitational field. 198/1 Clutch my ideas. When an electron, for example, passes through a photographic plate, it leaves a visible track behind it. This track, under close examination, is actually a series of dots. Each dot is a grain of silver formed by the electron's interaction with atoms in the photographic plate. When we look at the track under a microscope, it looks something like this. Ordinarily we would assume that one and the same electron, like a little baseball, went streaking through the photographic plate and left this trail of silver grains behind it. This is a mistake. Quantum mechanics tells us the same thing that Tantribuddhists have been saying for a millennium. The connection between the dots, the moving object, is a product of our minds, and it is not really there in rigorous quantum mechanical terms. The moving object, the particle with an Independent existence is an unprovable assumption. According to our custom of reasoning, wrote David Bohm, a professor of physics at Birkbeck College, University of London. We could suppose that the track of grains of silver indicates that a real electron moves continuously through space in a path somewhere near these grains, and by interaction caused the formation of the grams, but AC. According to the usual interpretation of the quantum theory, it would be incorrect to suppose that this really happened. All that we can say is that certain grains appeared, but we must not try to imagine that these grains were produced by a real object moving through space in the way in which we usually think of objects moving through space. For although this idea of a continuously moving object is good enough for an approximate theory, we would discover that it would break down in a very exact theory. 5. The natural assumption that objects, like particles, are real things that run their course in space and time according to causal laws, regardless of whether we are around to observe them or not, is repudiated by quantum mechanics. This is especially significant because quantum mechanics is the theory of physics. It has explained successfully everything from the particles U/199 subatomic particles to stellar phenomena. There never has been a more successful theory. It has no competition. Therefore, when we look at the tracks in a bubble chamber, we are left with the question, what made them? The best answer that physicists have so far is that particles are actually interactions between fields. A field, like a wave, is spread out over a much larger area than a particle. A particle is restricted to one point. A field, moreover, completely fills a given space, like the gravitational field of the Earth fills all of the space immediately around it. When two fields interact with each other, they interact neither gradually nor at all their areas of contact. Rather, when two fields interact, they do it instantaneously and at one single point in space, instantaneously and locally. These instantaneous and local interactions make what we call particles. In fact, according to this theory, these instantaneous and local interactions are particles. The continual creation and annihilation of particles at the subatomic level is the result of the continual interaction of different fields. This theory is called quantum field theory. Some major cornerstones of the theory were laid in 1928 by the English physicist Paul Dirac. Quantum field theory has been highly successful in predicting new types of particles and in explaining existing particles in terms of field interactions. According to this theory, a separate field is associated with each TVPE of particles, since only 3 types of particles were known in 1928. Only 3 different fields were required to explain them. The problem today, however, is that there are over 100 known particles, which, according to quantum field theory, require over 100 different fields. This abundance of theoretical fields is somewhat awkward, not to mention embarrassing, to physicists whose goal is to simplify nature. Therefore, most physicists have given up the idea of a separate field existing for each TVPE of particle. Nevertheless, quantum field theory is still an important theory, not only because it works, but also because it was the first theory to merge quantum mechanics and relativity, albeit in a limited way. All physical theories, including quantum theory, must satisfy the requirement of relativity theory that the laws of physics be independent of the state of motion of the observer attempts to integrate the theory of relativity with quantum theory, however, have been generally unsuccessful nonetheless. Both relativity and quantum theory are 200/I clutch my ideas required, and routinely used, in the understanding of particle physics. Their forced relationship is best described as strained, but necessary in this regard. One of the most successful integrations of the two is quantum field theory, although it covers only a relatively small range of phenomena. Quantum field theory is an ad hoc theory. That means that, like Bohr's famous specific orbits-only model of the atom, quantum field theory is a practical but conceptually inconsistent scheme. Some parts of it don't fit together mathematically. It is a working model designed around the available data to give physicists a place to stand in the exploration of subatomic phenomena. The reason that it has been around so long is that it works so well. Some physicists think that it may work too well. THEV fear that the pragmatic success of quantum field theory impedes the development of a consistent theory. Even with these well-known shortcomings, the fact is that quantum field theory is a successful physical theory, and it is premised on the assumption that physical reality is essentially non-substantial. According to quantum field theory, fields alone are real. They are the substance of the universe and not matter. Matter, particles, is simply the momentary manifestations of interacting fields which, intangible and insubstantial as they are the only real things in the universe. Their interactions seem particle-like because fields interact very abruptly and in very minute regions of space. Quantum field theory is, of course, an outrageous contradiction in terms. A quantum is an indivisible whole. It is a small piece of something, while a field is a whole area of something. A quantum field is the juxtaposition of two irreconcilable concepts. In other words, it is a paradox. It defies our categorical imperative that something be either this or that, but not both. The major contribution of quantum mechanics to Western thought, and there are many, be its impact on the artificial categories by which we structure our perceptions, since ossified structures of perception are the prisons in which we unknowingly become prisoners. Quantum theory boldly states that something can be this and that, a wave and a particle, S matrix theory quantum theory and relativity, but it provides limited information on the details of subatomic phenomena, and its current K is restricted to hadron interactions. Vlad's theory is discussed in the next chapter. The language of quantum theory is precise, but Taiki quantum theory does not state that something, like light for example 1, can be wave-like and particle. The particle zoo/201. It makes no sense to ask which of these is really the true description. Both of them are required for a complete understanding. In 1922, Werner Heisenberg, as a student, asked his professor and friend to be, Niels Bohr, if the inner structure of the atom is as close to descriptive accounts as you say, if we really lack a language for dealing with it, how can we ever hope to understand atoms? Bohr hesitated for a moment and then said, I think we may yet be able to do so, but in the process we may have to learn what the word understanding really means. 6. In human terms it means that the same person can be good and evil, bold and timid, a lion and a lamb. All of the above notwithstanding, particle physicists of any necessity analyze subatomic particles as if they were like little baseballs that fly through space and collide with each other. When a particle physicist studies a track on a bubble chamber photograph of a particle interaction, he assumes that it was made by a little moving object and that the other tracks on the photograph likewise were made by small moving objects. In fact, particle interactions are analyzed in much the same terms that can be applied to the collision of billiard balls. Some particles collide, and are annihilated in the process, and other newly created particles come flying out of the collision area. In short, particle interactions are analyzed essentially in terms of masses, velocities, and momenta. These are the concepts of Newtonian physics, and they also apply to automobiles and streetcars. Physicists do this because they have to use these concepts if they are to communicate at all. What is available to them is usually a black photograph with white lines on it. They know that 1. According to quantum theory, subatomic particles have no independent existence of their own. 2. Subatomic particles have wave-like characteristics as well as particle-like characteristics, and 3. Subatomic particles actually may be manifestations of interacting fields nonetheless. These white like at the same tune according to Burr's complementarity, page 93, light reveals either a particle-like aspect 1am wave-like aspect depending upon the context, i.e. the experiment. It is not possible to observe both the wave-like aspect and the particle-like aspect in the same situation. However, both of these mutually exclusive, complementary aspects are needed to understand HSHT. In this sense, light is both particle-like and wave-like. 202 / I clutch my ideas. Lines, more patterns, lend themselves to analysis in classical terms, and so that is how particle physicists analyze them. This dilemma, the dilemma of having to talk in classical terms about phenomena which cannot be described in classical concepts, is the basic paradox of quantum mechanics. It pervades every part of it. It is like trying to explain an LSD experience. We try to use familiar concepts as points of departure, but beyond that, the familiar concepts do not fit the phenomena. The alternative is to say nothing at all. Physicists who deal with the quantum theory, wrote Heisenberg, are also compelled to use a language taken from ordinary life. We act as if there really were such a thing as an electric current, or a particle, because, if we forbade all physicists to speak of electric current, or particles, they could no longer express their thoughts. 7. Therefore, physicists talk about subatomic particles as if they were real little objects that leave tracks in bubble chambers and have an independent, objective existence. This convention has been extremely productive over the last 40 years. Almost 100 particles have been discovered. They constitute what Kenneth Ford calls the particle zoo asterisk. The first thing to know about the particle zoo is that every particle of the same species looks exactly alike. Every electron looks exactly like every other electron. If you've seen one, you've seen them all. Likewise, every proton looks exactly like every other proton, every neutron looks exactly like every other neutron, and so on. Subatomic particles of the same type are absolutely indistinguishable. Subatomic particles of different types, however, can be recognized by their distinguishing characteristics, properties. The first distinguishing characteristic of a subatomic particle is its mass. A proton, for example, has about 1800 times more mass than an electron. This does not necessarily mean that a proton is 1800 times larger than an electron, since mass and size are not the same thing. A pound of lead and a pound of feathers have the same mass. When physicists refer to the mass of a particle, unless they * one of the finest popular books on particle physics is The World of Elementary Particles by Kenneth Ford, New York, Blaisdell, 1965. The particles U/203 indicate otherwise. They are referring to the mass of the particle. When it is at rest, the mass of a particle at rest is called its rest mass. Any mass other than a rest mass is called a relativistic mass, since the mass of a particle increases with velocity. A particle can have any number of relativistic masses. The size of a particle's relativistic mass depends upon its velocity. For example, at 99% of the speed of light, a particle's mass is 7 times larger than it is when the particle is at rest. At velocities above 99% of the speed of light, particle mass is increased dramatically. When the former electron accelerator at Cambridge, Massachusetts, was in operation, it received electrons from a small feeder accelerator. The electrons from the feeder accelerator were fed into the MAM accelerator. At 99,986 the velocity of light, the main accelerator then increased the velocity of these electrons to 999999996 the speed of light. This increase in velocity may look significant, but actually it is negligible. The difference between the initial velocity of the accelerated electrons and the final velocity of the accelerated electrons is the same as the difference in velocity between one automobile that can make a given trip in 2 hours and a faster automobile that can make the same trip in 1 hour 59 minutes and 59 seconds. 8. The mass of each electron, however, increased from 60 times to as much as 11,800 times the electron rest mass. In other words, particle accelerators are misnamed. They do not increase the velocities of subatomic particles, the definition of acceleration, as much as they increase their mass. Particle accelerators are actually particle enlargers, massifiers. The masses of particles, whether at rest or in motion, are measured in electron volts. An electron volt has nothing to do with electrons. An electron volt is a unit of energy. It is the energy acquired by any particle with 1 unit of charge falling through a potential difference of 1 volt. The point is that to measure something in terms of electron volts is to measure its energy, yet this is precisely the unit of measurement that particle physicists use to measure a particle's mass. For example, the rest mass of an electron is 51 million electron volts, MeV, and the rest mass of a proton is 938 million electron volts. The transformation of mass into energy and energy into mass is such a routine phenomenon in particle physics that particle physicists employ units of energy to designate a particle's mass. Mass is only one particular form of energy. Page 154. The 204 / I clutch my ideas. Energy of being. If a particle is moving, it not only has energy of being, its mass, but it also has energy of motion, kinetic energy. Both types of energy can be used to create new particles in a particle collision. Often it is easier to compare a particle's mass with the lightest massive particle, the electron, instead of referring to the number of electron volts it contains. This arrangement makes the mass of an electron 1 and the mass of a proton, for example, 1836.12. Using this system, the mass of any particle tells immediately how much heavier it is than an electron. This is the system that is used in the table at the back of the book. When physicists listed all the known particles by the order of their masses, from the lightest to the heaviest, they discovered that subatomic particles fall into roughly 3 categories: the lightweight particles, the medium-weight particles, and the heavyweight particles. When it came to naming these categories, however, they unaccountably lapsed into Greek again. The group of lightweight particles they called leptons, which is Greek for the light ones. The group of medium-weight particles they called mesons, which is Greek for the medium-sized ones. The group of heavyweight particles they called baryons, which is Greek for the heavy ones. Why physicists did not call these new groups light, medium and heavy is one of the unanswerable questions of physics. Since the electron is the lightest material particle, it is, of course, a lepton. The proton is a heavyweight particle, a baryon, although it is the lightest of the heavyweight particles. Most subatomic particles are classified in this way, but not all of them, which brings us to a phenomenon of particle. Einstein's formula E equals m2 says that mass is energy, energy is mass. Therefore, strictly speaking, mass is not a particular form of energy. Every form of energy is mass. Kinetic energy, for example, Ts mass. As we speed up a particle, and hence give it energy, it gains mass. In exactly the amount required. A equals, C2. Wherever energy goes, mass goes. Physicists no longer use the terms leptons, mesons and baryons to refer to particle mass alone. These terms now refer to classes of particles which are defined by several properties in addition to mass. For example, the tan particle, T, which was discovered by a joint team from the Stanford Linear Accelerator Center, SLAC, and the Lawrence Berkeley Laboratory, LBL, in 1975, seems to be a lepton even though it has more mass than the heaviest baryon. Similarly, the D particles, also discovered by a joint SLAC/LBL team in 1976, are mesons even though they have more mass than the tan particle. The particles U/205. Physics which, like much of quantum mechanics, escapes the bounds of concept. A few particles do not fit into the lepton meson-baryon framework. Some of them are well known, like the photon, and others have been theorized but not discovered yet, like the graviton. All of them have in common the fact that they are massless particles. Wait a minute, we exclaim. What is a massless particle? A massless particle, says Jim DeWitt, who has studied this phenomenon, is a particle that has zero rest mass. R of its energy is energy of motion. When a photon is created, it instantly is traveling at the speed of light. It cannot be slowed down, it has no mass to slow, and it cannot be speeded up. Nothing can travel faster than the speed of light. Massless particle is an awkward translation from mathematics to English. Physicists know exactly what they mean by a massless particle. A massless particle is the name they give to an element in a mathematical structure. What that element represents in the real world, however, is not so easy to describe. In fact, it is impossible because the definition of an object, like a particle, is something that has mass. Zen Buddhists have developed a technique called the cone, which, along with meditation, produces changes in our perceptions and understanding. A cone is a puzzle which cannot be answered in ordinary ways because it is paradoxical. What is the sound of one hand clapping? Is a Zen cone. Zen students are told to think unceasingly about a particular cone until they know the answer. There is no single correct answer to a cone. It depends upon the psychological state of the student. Paradoxes are common in Buddhist literature. Paradoxes are the places where our rational mind bumps into its own limitations. According to Eastern philosophy in general, opposites, such as good bad, beautiful ugly, birth death, and so on, are false distinctions. One cannot exist without the other. They are mental structures which we have created. These self-made and self-maintained illusions are the sole cause of paradoxes. To escape the bonds of conceptual limitation is to hear the sound of one hand clapping. Physics is replete with cones, i.e., picture a massless particle. Is it a coincidence that Buddhists exploring internal reality a millennium ago and physicists exploring external reality a millennium later both discovered that understanding involves passing the barrier of paradox? 206 / I clutch my ideas. The second characteristic of a subatomic particle is its charge. Every subatomic particle has a positive, a negative, or a neutral charge. Ik charge determines how the particle will behave in the presence of other particles. If a particle has a neutral charge, it is utterly indifferent to other particles. Regardless of what charge they have. Particles with positive and negative charges, however, behave quite defiant of toward each other. Positively and negative charged particles are attracted to particles with the opposite sign and repelled by particles with the same sign. Two positively charged particles, for example, find each other's company quite repulsive and immediately put as much distance between themselves as possible. The same is true of two negatively charged particles. A negatively charged particle and a positively charged particle, on the other hand, are irresistibly attracted to each other, and they immediately move toward one another if they are able to do so. This dance of attraction and repulsion between charged particles is called the electromagnetic force. It enables atoms to join together to form molecules, and it keeps negatively charged electrons in orbit around positively charged nuclei at the atomic and molecular level. It is the fundamental glue of the universe. Electronic charge comes only in one fixed amount. A subatomic particle can have no electrical charge, neutral, or one unit of electrical charge, either positive or negative, or, in certain instances, 2 units of electrical charge, but nothing in between. There is no such thing as a particle with 1 and 1/4 units of electrical charge, or a particle with 1/7 units of electrical charge. Every subatomic particle has either one whole Unit of electrical charge, 2 whole units of electrical charge. Or no electrical charge at all, in other words. Like energy. Planck's discovery, electrical charge is quantized, it comes in chunks. In the case of electrical charge, all of the chunks are the same. So why this is so is one of the unanswered questions in physics. Asterisk. When the characteristic of charge is added to the characteristic of mass, a particle personality, so to speak, begins to emerge. An electron, for example, is the only subatomic particle with a rest mass of 51 million electron volts and an Ega. Tin's peculiar aspect of Elkfentalkleorgt appears to be connected to the unknown properties of quarks and / magnetic monopoles. The particles U /207 charge. With this information, a particle physicist knows not only how massive an electron is, he also knows how it will interact with other particles. The third characteristic of a subatomic particle is its spin. Subatomic particles spin about a theoretical kind of axis like a spinning top. One big difference between a spinning top and a spinning particle, however, is that a top can spin either faster or slower, but a subatomic particle always spins at exactly the same rate. Every electron, for example, always spins at exactly the same rate as every other electron. The rate of spin is such a fundamental characteristic of a subatomic particle that if it is altered, the particle itself is destroyed. That is, if the spin of a particle is altered, the in question is changed so fundamentally that it no longer can be considered an electron, or a pion, or whatever it was before we altered its spin. This makes us wonder whether all of the different particles might be just different states of motion of some underlying structure or substance. This is the basic question of particle physics. Phenomenon in quantum mechanics has a quantum aspect makes it discontinuous. This is also true of spin. Spin is quantized just like energy and charge. It comes in chunks like charge. All of the chunks are the same size. In other words, when a spinning top slows down its rotation, does not diminish smooth k and continuously, but in a series of TMV steps. These steps are so small and close together that it is impossible to observe them. The top appears to spin more and more slowly until it stops spinning altogether, but actually the process is very jerky. It is as if the top could spin, by some strange law that nobody understands, only at 100 revolutions per minute, 90 revolutions per minute, 80 revolutions per minute, and so on, with absolutely no exceptions in between. If our hypothetical top wants to spin slower than 100 revolutions per minute, it must jump all the way down to the next slower speed of 90 revolutions per minute. This is analogous to the situation with subatomic particles, except that 1. Particular types of particles forever spin at the same speed, and 2. The spin of subatomic particles is calculated in terms of angular momentum. Angular momentum depends upon the mass, size, and rate of rotation of a spinning object. More of any one of these properties increases the angular momentum of the object. In 208 I clutch my ideas. General, angular momentum is the strength of the rotation, or put another way, the effort required to stop the rotation. The more angular momentum an object has, the more effort is required to stop it from spinning. A spinning top does not have much angular momentum, because it is small and it has little mass. A merry-go-round, in comparison, has an enormous angular momentum, not because it rotates very fast, but because it is large and it has so much mass. Now that you understand spin, forget everything that you have just learned except the bottom line, angular momentum. Every subatomic particle has a fixed, definite, and known angular momentum, but nothing is spinning if thou don't understand. Don't worry, physicists don't understand these words, either they just use them. If you try to understand them, they become a cone, asterisk. The angular momentum of a subatomic particle is fixed, definite, and known, but wrote Max Born. One should not imagine that there is anything in the nature of matter actually rotating. 9. Said another way, the spin of a subatomic particle involves the idea of a spin without the existence of something spinning. Ln even Born had to admit that this concept is rather abstruse. Rather 13, nonetheless, physicists use this concept because subatomic particles do behave as if they have angular momentum, and that angular momentum has been determined to be fixed and definite in each case because of this. In fact, spin is one of the major characteristics of subatomic particles. The angular momentum of a subatomic particle is based upon our old friend, Planck's constant, page 51. Remember that Planck's constant, which physicists call the quantum of the quantitative, mathematical, description of particle spin is not any more understandable than the non-quantitative description Dr. Felix Smith, head of molecular physics, Stanford Research Institute, once related to me the true story of a physicist in and who worked at Los Alamos after World War II. Seeking help on a difficult problem, he went to the great Hungarian mathematician John von Neumann, who was at Los Alamos as a consultant. Simple, said von Neumann, this can be solved using the method of characteristics. After the explanation, the physicist said, I'm afraid I don't understand the method of characteristics. Young man, said von Neumann, in mathematics you don't understand things, you just get used to them. The particles U/209. Action was the discovery that set into motion the revolution of quantum mechanics. Planck discovered that energy is emitted and absorbed not continuously, but in small packages, which he called quanta. Since that initial discovery, Planck's constant, which represents the quantized nature of energy emission and absorption, has appeared again and again as an essential element in the understanding of subatomic phenomena. 5 years after Planck's discovery, Einstein used Planck's constant to explain the photoelectric effect, and later still he used it to determine the specific heat of solids, an area far removed from Planck's original study of black-body radiation. Burr discovered that the angular momentum of electrons as they orbit atomic nuclei is a function of Planck's constant. De Broglie used Planck's constant to calculate the wavelength of matter waves, and it is a central element in Heisenberg's uncertainty principle. As important as Planck's constant is in the realm of subatomic particles, however, it is entirely unobservable in the world at large. This is because the psi/e of the packages by which energy is emitted and absorbed is so small that energy at our gross level appears to be one continuous flow, similar k, because the indivisible unit of angular momentum is so small, it, too, cannot be observed in the macroscopic world. A spectator Swivelmg in his chair at a tennis match has 100000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000times more angular momentum than an electron. Put another way, a change of 1 penny in the gross national product of the United States is a disturbance more than a billion times greater than a change by 1 unit of the spectator's angular momentum. 12. Instead of writing out the actual angular momentum of a subatomic particle, physicists usually indicate the spin of a subatomic particle BV, comparing it to the spin of a photon, whose spin they call 1. This system has revealed yet an other unexplainable pattern of subatomic phenomena. Entire families of particles have similar spin characteristics. The entire family of leptons, the lightweight particles, for example, has a spin of /2, which means that THEV all have an angular momentum which is v4 of a photon's angular momentum. The same is true for the entire family of baroids, the heavyweight particles. The mesons also have peculiar spin characteristics. They spin in such a way that their angular momenta is always either 0, 1, 2, 3, etc. in relation to the angular momentum of a photon, but nothing in between. 0 equals no spin, 1 equals the same. 210/1 Clutch my ideas. Angular momentum as a photon, 2 equals twice the angular momentum of a photon, etc. The spin characteristics of all of the families and all of the particles are in the table at the back of the book. The values of a particle's charge, spin and other major characteristics are represented by specific numbers. These numbers are called quantum numbers. Every particle has a set of quantum numbers which identify it as a particular type of particle. Every particle of a particular type has the same set of quantum numbers as every other particle of the same type. Every electron, for example, has the same quantum numbers as every other electron. An electron's quantum numbers, however, distinguish it from protons, all of which also have the same quantum numbers. Individual particles don't have much personality, in fact, they don't have any personality at all. When Dirac imposed the requirements of relativity on quantum theory, his formalism indicated the existence of a particular positively charged particle. Since the only positively charged particle known in those days, 1928, was the proton, Dirac, and most other physicists, assumed that his theory had accounted, mathematically, for the proton. His theory even was criticized for yielding the wrong proton mass. Upon closer examination, however, it became evident that Dirac's theory described not the proton, but an entirely different particle. Dirac's new particle was like an electron except that its charge and some of its other major properties were exactly opposite to those of an electron. In 1932, Carl Anderson, at Caltech, who hadn't heard of Dirac's theory, actually discovered this new particle and called it a positron. Physicists later discovered that every particle has a counterpart which is exactly like it but opposite in several major respects. This new class of particles was called antiparticles. An antiparticle, despite its name, is a particle. The antiparticle of an antiparticle is another particle. Some particles have other particles as antiparticles. For example, a positive pi meson is the antiparticle of a negative pi meson, and the other way round. A few particles are their own antiparticles, like the photon. All of the particles and their antiparticles are in the table at the back of the book. Asterisk. The basic quantum numbers are spin, isotopic spin, charge, strangeness, charm, Barroyan number and lepton number. The particles U/211. The meeting of a particle and its antiparticle is always spectacular. Whenever a particle and its antiparticle meet, they annihilate each other. When an electron meets a positron, for example, both of them disappear and in their place are two photons which instantly depart the scene at the speed of light. The particle and the antiparticle literally disappear in a puff of light. Conversely, particles and antiparticles can be emitted out of energy and always in pairs. The universe is made of both particles and antiparticles. Our part of it, however, is made almost entirely of regular particles which combine into regular atoms to make regular molecules which make regular matter, which is what we are made of. Physicists speculate that in other parts of the universe, antiparticles combine into anti-atoms to make antimolecules, which make antimatter, which is what antipeople would be made of. There are no antipeople in our part of the universe, because, if there were, they all long since have disappeared in a flash of light. Leptons, mesons, baroias, mass, charge, spin, and anti-particles are some of the concepts that physicists use to categorize subatomic phenomena when they momentarily assume that subatomic particles are real objects that move through space and time. These concepts are useful, but only in a limited context. That context is when physicists, for convenience, pretend, as we all do, that dancers can exist apart from a dance. Chapter 1. The dance. The dance of subatomic particles never ends, and it is never the same. However, physicists have found a way to diagram the parts of it that interest them. The simplest drawing of any type of movement is a space map. A space map shows the location of things in space. The map, for example, first drawing, next page, shows the positions of San Francisco, California and Berkeley, California. The vertical axis is the north-south axis, as on any map, and the horizontal axis is the east-west line. The map also shows the path of a helicopter flying between San Francisco and Berkeley, and, on a greatly enlarged basis, it shows the path of a proton traveling around the cyclotron at the Lawrence Berkeley Laboratory. Like all road maps, this space map is two-dimensional. It shows how far north, the first dimension, and how far east, the second dimension, Berkeley is of San Francisco. It does not show the altitude of the helicopter, the third dimension, and it does not indicate how much time, the fourth dimension, the flight from San Francisco to Berkeley required. If we want to show the time involved in the San Francisco-Berkeley flight, we must draw a space-time map. A space-time map, second drawing, next page, shows the positions of things in space, and it also shows their positions in time. The vertical axis on a space-time map is the time axis. Space-time maps are read from the bottom up because the passage of time is represented by movement up the time axis. The horizontal axis of a space-time map is the space axis, which 212. The dance /21-3 shows the movement of objects in space. The path traced by an object on a space-time map is called its world line. For example, the space-time map below shows the same flight from San Francisco to Berkeley. North, west, San Francisco, east, time, space. Initially the helicopter is sitting on the ground in San Francisco. Its world line is vertical, because, although it is not moving in space, it is moving in time. A to B is the world line of the helicopter while it sits on its pad in San Francisco. When the helicopter takes off for Berkeley, it moves forward, both in time and space, and its world line traces the path on the space-time map between B and C. When it lands in Berkeley, its world line is vertical once again because it no longer moves in space, but, like all things, it continues to move in time, C to D. The arrowheads show which direction the helicopter is moving. It can move backward and forward in space, but, of course, it only can move forward in time. The dashed lines show the world lines of San Francisco and Berkeley. 214/1 Clutch my ideas. Which do not move in space at all except during California earthquakes. Physicists use similar space-time maps to diagram particle interactions. Below is a space-time diagram of an electron emitting a photon. Time, space. Starting at the bottom, an electron moves through space with a certain velocity. At the point in space and time indicated by the dot, it emits a photon. The photon flies off at the speed of light to the right, and the electron, its momentum, affected by the emission of the photon, alters course and moves off more slowly to the left. In 1949, Richard Feynman discovered that space-time maps like these have an exact correspondence with mathematical expressions which give the probabilities of the interactions that they depict. Feynman's discovery was an extension of Dirac's 1928 theory, and it helped to evolve that theory into the quantum field theory that we know today. Therefore, this type of diagram is sometimes called a Feynman diagram. Ongmal diagrams of this sort y space-time diagrams, however, Feynman also discovered that in menug space descriptions, which are complementary to space-time descriptions, y closely approximate the actual conditions of a collision experiment, the basic concept of space-time descriptions. And momentum energy space descriptions is the same, except that momentum energy space descriptions deal with the momenta and energies of the particles involved instead of then space-time coordinates. The diagrams of both space-time descriptions and momentum energy space descriptions are similar except the dance /2I5. Here is a Feynman diagram of a particle /antiparticle annihilation. An electron on the left approaches an anti-electron, a positron, which is coming from the right. At their point of contact, indicated by the dot, they mutually annihilate each other, and two photons are created which depart in opposite directions at the speed of light. Electron, e.g. positron, a happening in the subatomic world is called an event, Events are indicated in Feynman diagrams by dots. Every subatomic event is marked by the annihilation of the initial particles and the creation of new ones. This is true for every event and not only those involving particles and antiparticles. With this in mind, we now can look at the particle diagram on page 214 again, and see it in a different light. Instead of saying that an electron moving through space emitted a photon, which changed the electron's momentum, we can say as well that an electron moving through space emitted a photon and went out of existence at that point. A new electron was created in this process and it departed the scene with a new momentum. There is no way of knowing if this interpretation is correct or not because all electrons are identical. However, it is simpler and more consistent to assume that the original particle was annihilated and a new particle was created. The indistinguishability of subatomic particles makes this possible. That diagrams depicting momentum energy space descriptions can be rotated. As we shall see, accurately speaking, the remaining Feynman diagrams in this book depict momentum energy space descriptions unless they are specifically identified as space-time diagrams. A detailed analysis of the dot in this particular diagram would equal a two-step process in which first one photon and then the other is emitted technically. Diagrams with more than 3 lines connected to the same vertex are called Mandelstam diagrams. 216/1 Clutch my ideas. Here is a Feynman diagram of the process that we discussed. On page 196. A negative pi meson collides with a proton and the two particles are annihilated. Their energy of being, mass, and energy of motion create 2 new particles, a lambda particle and a new K meson. These 2 new particles are unstable and live less than a billionth of a second before they decay into other particles. Actual decay times are in the table at the back of the book. The neutral K meson decays into a positive pi meson and a negative pi meson, the lambda particle, and this is the interesting part, decays into the original 2 particles, a negative pi meson and a proton. It is as if we smash 2 toy. The dance /217 automobiles together, and instead of shattering into bits and pieces, they come apart into more toy automobiles, some of which are as large as the originals. Subatomic particles forever partake of this unceasing dance of annihilation and creation. In fact, subatomic particles are this unceasing dance of annihilation and creation. This 20th century discovery, with all its psychedelic implications, is not a new concept. In fact, it is very similar to the way that much of the Earth's population, including the Hindus and the Buddhists, view their reality. Hindu mythology is virtually a large-scale projection into the psychological realm of microscopic scientific discoveries. Hindu deities such as Shiva and Vishnu continually dance the creation and destruction of universes, while the Buddhist image of the wheel of life symbolizes the unending process of birth, death, and rebirth, which is a part of the world of form, which is emptiness, which is form. Imagine that a group of young artists have founded a new and revolutionary school of art. Their paintings are so unique that they have come to share them with the creator of an old museum. The curator regards the new paintings, nods his head, and disappears into the vaults of the museum. He returns, carrying some very old paintings, which he places beside the new ones. The new art is so similar to the old art that even the young artists are taken aback. The new revolutionaries, in their own time and in their own wealth, have rediscovered a very old school of painting. Let us look again at the Feynman diagram of an electron positron annihilation. Suppose that we use the arrowhead to indicate which is the particle, the electron, and which is the antiparticle, the positron, by making the arrowheads that point up indicate the particles and the arrowheads that point down indicate the antiparticles. That would make the diagram on page 215 look like the drawing on page 218. Naturally, time, as we experience it, only travels in one direction, forward, and that is up on a space-time diagram. Nonetheless, this simple convention would give us an easy way of telling particles from antiparticles. World lines that appear to move forward in time would belong to particles, and world lines that appear to move backward in time would belong to antiparticles. Photons would not have arrowheads because they are their own antiparticles. 218/1 Clutch my ideas. Electron, E tilde, positron, E asterisk. Feynman demonstrated in 1949 that this convention is more than an artistic device. He discovered that a positron field propagating forward in time is mathematically the same as an electron field propagating backward in time. In other words, according to quantum field theory, an antiparticle is a particle moving backward in time. An antiparticle does not have to be considered as a particle moving backward in time, but that is the simplest and most symmetric way of viewing antiparticles. For example, because the arrowheads distinguish the particles from the antiparticles, we can twist the original Feynman diagram around into any position that we choose and still be able to distinguish the one from the other. Here are some different ways that we can twist the original Feynman diagram. Each of these variations is a separate diagram and represents a particle /antiparticle interaction. By twisting the original diagram completely around, we can represent every asterisk. These three interactions are, left, a photon and an electron annihilate and create a photon and an electron, electron-photon scattering, middle, two photons annihilate to create a positron and an electron, positron-electron pair creation, and, rig /if, a positron and a photon annihilate to create a positron and a photon. Positron-photon scattering. The dance /219. Possible interaction between an electron, a positron, and two photons. The precision, simplicity, and symmetry of Feynman diagrams make them a special type of poetry. Below is a space-time diagram of two events. A collision between two photons at B creates an electron-positron pair, and, subsequently, an electron and a positron annihilate each other and create two photons at A. The left half of this diagram, the interaction at A, is the same as the electron-positron annihilation on page 218. Ordinarily we would interpret these events as follows: 2 photons collide in the lower right of the diagram, producing an electron-positron pair. The electron flies off to the right while the positron flies off to the left, where it meets another electron which has entered the diagram from the lower left. There, they mutually annihilate and create two photons which depart in opposite directions. The preferred interpretation of quantum field theory, however, is much simpler. In it there is only one particle. That particle, an electron, enters the diagram from the lower left and travels forward in time and space until it emits 2 photons at a. This causes it to reverse its direction in time, traveling 220 / I clutch my ideas. Backward in time as a positron. It absorbs 2 photons at B, reverses its direction in time again, and Agdin becomes an electron instead of 3 particles. There is only one particle, which, moving from left to right, travels first forward in time, then backward in time, and then forward in time again. This is the static type of space-time picture described in Einstein's theory of relativity, page 150. If we could survey an entire span of time as we can survey an entire region of space, we would see that events do not unfold with the flow of time but present themselves complete, like a finished painting, on the fabric of space-time. In such a picture, movements backward and forward in time are no more significant than movements backward and forward in space. The illusion of events developing in time is due to our particular type of awareness, which allows us to see only narrow strips of the total space-time picture one at a time. For example, suppose that we place a piece of cardboard with D narrow strip cut out of it over the diagram on page 219 so that all that we can see of the interaction is what is visible through the cutout. If we move the cardboard slowly upward, starting at the bottom, our restricted view discovers a series of events, each one happening after the other. First, we see 3 particles, 2 photons entering our view from the right and an electron entering from the left, 1. Next, we see the photons collide to produce an electron-positron pair, the electron flying off to the right and the positron flying off to the left. 2. Finally, we see the newly created positron meet the original electron to create 2 new photons. 3. Only when we remove the entire cardboard, which was an artificial construction anyway, can we see the complete picture. In space-time, wrote de Broglie, everything which for each of us constitutes the past, the dance /221, present and the future is given in block. Each observer, as his tune passes, discovers, so to speak, new slices of space-time which appear to him as successive aspects of the material world, though in reality the ensemble of events constituting space-time exist prior to his knowledge of them. Wait a minute, says Jim DeWitt to a passing particle physicist. It is easy to talk of movement backward and forward in time, but I never have experienced going backward in time. If particles can travel backward in time, WHV can't / travel backward in time. 1 asterisk. The answer which physicists gave to this question is actually quite simple. There is a growing tendency and closed part of the Unofficial-Se. Then explanation goes, for disorder, called entropy, to expand at the price of order, called negentropy. Suppose, for example, that we deposit a drop of black ink into a glass of clear water. Initially its presence is quite ordered. That is, all of the molecules of ink are located in one small area and are clean segregated from the molecules of clear water. As time passes, how /EI, natural molecular motion will cause the black ink molecules steadily to intersperse with the clear water molecules until they are distributed E /N throughout the glass, resulting in a murky homogeneous liquid with no structure or whatever, on of a bland uniformity, maxi. Mal entropy. Experience has taught us to associate MCI easing entropy with the forward movement of time if see a movie of a glass of murky water becoming clearer and clearer until all of the foreign substance in it collects into one small drop at the top. We know at once that the film is running back/hard of course it is theoretically possible for this to happen, but it is so improbable that it simply never, probably, will happen in short time flows in the direction of high probability, which is the direction of increasing entropy. The theory of growing disorder or increasing entropy is called the second law of thermodynamics. The second law of thermodynamics is statistical, that means it won't work unless there are entities in a given situation to apply it to. Generally speaking, individual subatomic particles are conceived as such conceptually isolated, short-lived entities that the second 222 / I clutch my ideas. L.W. of thermodynamics does not apply to the *T. It does apply, however, to molecules which are quite complex compared to subatomic particles, to living cells which are more complex than molecules, and to people who are made of billions of cells. It is only at the subatomic, or quantum level, that the forward flow of time loses its significance. However, there is speculation, and some evidence, that consciousness, at the most fundamental level/CLS for a quantum process, the dark adapted EC for example, can detect a single photon. If this is so, then it is conceivable that BV expanding OUI awareness to include functions which normally he beyond its parameters, the way yogis control their body temperature and pulse rate, we can become aware of, experience these processes themselves // at the quantum level. The flow of time has no meaning, and if consciousness is fundamentally a similar process, and // we can become aware of these processes within ourselves, then it also is conceivable that we can experience timelessness. If we can experience the most fundamental functions of our psyche, and if they are quantum in nature, then it is possible that the ordinary conceptions of space and time might not apply to them at all, as they don't seem to apply in dreams. Such an experience would be difficult to describe rationally. Infinity in a gram of sand / and eternity in an hour, but it would be very real indeed. For this reason, reports of time distortion and timelessness from gurus in the East and LSD trippers in the West ought not perhaps to be discarded peremptorily. Subatomic particles do not just sit around being subatomic particles, they are beehives of activity. An electron, for example, constantly is emitting and absorbing photons. These photons are not full-fledged photons, however they are a now thou see it now you don't // they are exactly like real photons, except that they don't fly off on their own. They are reabsorbed by the electron almost as soon as they are emitted. Therefore, they are called virtual photons. Virtual means being so in effect or essence, although not in actual. The aged lawn theory of very high is an artifact of the mesurement process. The dance / 223. Fact, they are virtually photons. The only thing that keeps them from being full-fledged photons is their abrupt absorption by the electron that emits them *. In other words, first then is an electron, then there is an electron and a photon, and then Psi is an electron again. This situation is of course a violation of the conservation law of mass energy / the conservation law of mass energy says, in effect, that we cannot get something for nothing. According to quantum field theory, however, we do get something for nothing, but only for about 1000 millionth, 10^15 of a second t. The reason that this can happen according to the theory is the famous Heisenberg uncertainty principle. That Heisenberg uncertainty principle, as it originally was formulated, says that the more certain we are of the position of a particle, the less certain we can be about its momentum, and the other /AV round we can determine its position precise k, but in that east we cannot determine its momentum at all if we choose to measure its momentum precisely. Then we will not be able to know where it is located. Page 111. In addition to the reciprocal uncertainty of position and momentum, there also is a reciprocal uncertainty of time and energy. The less uncertainty there is about the time involved in a subatomic event, the more uncertainty there is about the energy involved in the event, and that other way round. A measurement as accurate as 1000 millionth of a second leaves very little uncertainty about the time involved in the emission and absorption of a virtual photon. It does, however, cause a specific uncertainty about how much energy was involved. Because of this uncertainty the balance books kept BV the conservation law of mass energy are not upset, said. From 1 point all /it until photons differ from ital ones in that the rest mass is not zero on k0 rest mass photons can escape their outvows of looking at ventnal photons mathematical in the HRST, old tishand perturber. Lion the that mass of a /ertnal patilt is that same as tin in SS of a equal particle, but tmrg is not consent d in that second, fe nan perturbation. Theon, enet momentum is exactly conserved, but the /utnit particles do not have fcl in is. T in a typical atomic process, high energy virtual photons ha /tt/tn shorter lived turns. Feet. The point is that space is not real k nothing empty but has infinite en *rg according to Sarfati a virtual process gets tnggt red bva superlumal taster than light jump of trop information, which briefly organizes some of this infinite assume energy to make the virtual particle s. 224 / I clutch my ideas. Another way, the event happens and is over with so quickly that the electron can get away with it. It is as if the policeman who enforces the conservation law of mass energy turns his hack on violations if they happen quickly enough. However, the more flagrant the violation, the more quickly it must happen. If we provide the necessary energy for a virtual photon to become a real photon without violating the conservation law of mass energy, it does just that. That is why an excited electron emits a real photon. An excited electron is an electron that is in an energy level higher than its ground state. An electron's ground state is its lowest energy level. Why? It is as close to the nucleus of an atom as it can get. The only photons that electrons emit when they are in their ground state are virtual photons, which they immediately reabsorb so as not to violate the conservation law of mass energy. An electron considers the ground state to be its home. It doesn't like to leave home. In fact, The on-off time it leaves its ground state is when it literally is pushed out of it with extra energy. In that case, the electron's first concern is to get back to its ground state, provided that it hasn't been pushed so far from the nucleus that, in effect, it becomes a free electron. Since the ground state is a low energy state, the electron must lose its excess energy before it can return to it. Therefore, when an electron is at an energy level higher than its ground state, it jettisons its excess energy in the form of a photon. The jettisoned photon is one of the electron's virtual photons that suddenly finds itself with enough energy to keep going, without violating the conservation law of mass energy, and it does. In other words, one of the electron's virtual photons suddenly is promoted to a real photon. The amount of energy, the frequency, of the promoted photon depends upon how much excess energy the electron had to jettison. The discovery that electrons emit only photons of certain energies and no others is what made the quantum theory or the quantum theory. Electrons are always surrounded by a swarm of virtual photons. If two electrons come close enough to each other, close enough so that their virtual photon clouds overlap, it is possible that a virtual photon that is emitted from one electron will be absorbed by the other electron. Below is a Feynman diagram. There are other virtual particles in that cloud of virtual particles sun-minding an electron, but photons are the most common among them. The dance /225 of a virtual photon being emitted by one electron and absorbed by another electron. The closer the electrons come to each other, the more this phenomenon occurs. Of course, the process is two-way, with both electrons absorbing virtual photons that were emitted by the other. This is how electrons repel each other. The closer two electrons come, the more virtual photons they exchange. The more virtual photons they exchange, the more sharply their paths are deflected. The repulsive force between them is simply the cumulative effect of these exchanges of virtual photons, the number of which increases at close range and decreases at a distance. According to this theory, there is no such thing as action at a distance, only more and fewer exchanges of virtual photons. These interactions, absorptions and emissions, happen on location, so to speak, right there where the particles involved are located. The mutual repulsion of two particles of the same charge, like two electrons, is an example of an electromagnetic force. In fact, according to quantum field theory, an electromagnetic force is the mutual exchange of virtual photons. Physicists like to say that the electromagnetic force is mediated by photons. Every electrically charged particle continually emits. However, the essence of quantum lines stems to demand a non-dynamic action at a distance operating faster than light. A good example of this is the Pauli exclusion principle, which indicates a correlation between the motions of two electrons over and above the exchange of virtual signal photons. Other examples, EPR and Bell's theorem, are discussed in a later chapter. 226 / I clutch my ideas and reabsorbs virtual photons and / or exchanges them with other charged particles. When two electrons, two negative charges, exchange virtual photons, they repulse each other. The same thing happens when two protons, two positive charges, exchange virtual photons. When a proton and an electron, a positive charge and a negative charge, exchange virtual photons, they attract each other. Therefore, since the development of quantum field theory, physicists generally have substituted the word interaction for the word force. An interaction is when anything influences anything else, in this context, a mutual exchange of virtual photons. It is a more precise term than force, which labels that which happens between electrons but does not say anything about it. That part of quantum field theory, Dirac's original part, which deals with electrons, photons, and positrons, is called quantum electrodynamics. Virtual photons, even if they were charged particles, would not be visible in a bubble chamber because of their extremely short lives. Their existence is inferred mathematical. Therefore, this extraordinary theory that particles exert a force on each other by exchanging other particles clearly is a free creation of the human mind. Page 8. It is not necessarily how nature really is. It is only a mental construction which correctly predicts what nature probably is going to do next. There might be and probably are other mental constructs that can do as good a job as this one or better, although physicists have not been able to think of them. The most that we can say about this or any other theory is not whether it is true or not, but only whether it works or not, that is, whether it does what it is supposed to do. Quantum theory is supposed to predict the probabilities of given subatomic phenomena to occur under certain circumstances, even though quantum field theory as a whole is not totally consistent. The pragmatic reality is that it works. There is a Feynman diagram for every interaction, and every Feynman diagram corresponds to a mathematical formula which precisely predicts the probability of the diagrammed interaction to happen. In 1935, Hideki Yukawa, a graduate student in physics, in ACT, there usually is an infinite series of Feynman diagrams for every interaction. The dance /227 decided to apply the new virtual particle theory to the strong force. The strong force is the force that keeps atomic nuclei together. It has to be strong because the protons which along with the neutrons make up the nucleus of an atom naturally repel each other, being particles of like sign. Positive protons want to be as far away from each other as they can get. This is because of the electromagnetic force between them. However, within the nucleus of an atom, these mutually repulsive protons not only are kept in close proximity, but they also are bound together very tightly. Whatever is binding these protons together into a nucleus, physicists reasoned must be a very strong force compared to the electromagnetic force, which works against it. Therefore, they decided to call the strong force, naturally, the strong force. The strong force is well named because it is 100 times stronger than the electromagnetic force. It is the strongest force known in nature. Like the electromagnetic force, it is a fundamental glue, i.e., electromagnetic force holds atoms together externally with each other to form molecules, and internally it binds electrons to their orbits around atomic nuclei. The strong force holds the nucleus itself together. The strong force is somewhat muscle-bound, so to speak. Although it is the strongest force known in nature, it also has the shortest range of all the forces known in nature. For example, as a proton approaches the nucleus of an atom, it begins to experience the repulsive electromagnetic force B between itself and the protons within the nucleus, the closer the free proton gets to the protons in the nucleus, the stronger the repulsive electromagnetic force between them becomes. At 1/3 the original distance, for example, the force is 9 times as strong. This force causes a deflection in the path of the free proton. The deflection is a gentle one if the proton is distant from the nucleus, and very pronounced if the proton should come close to the nucleus. However, if we push the free proton to within about 1/10 of a centimeter of the nucleus, it suddenly is sucked into the nucleus with a force 100 times more powerful than the repulsive electromagnetic force. 1/10 of a centimeter is about the psi/e of the proton itself. In other words, the proton is relatively unaffected by the strong force, even at a distance only slightly greater than 228 I clutch my ideas. Its own magnitude closer than that, however, and it is completely overpowered by the strong force. Yukawa decided to explain this powerful but very short range strong force in terms of virtual particles. The strong force theorized Yukawa is mediated by virtual particles, like the electromagnetic force is mediated by virtual photons according to Yukawa's theory, just as the electromagnetic force is the exchange of virtual photons. The strong force is the exchange of another type of virtual particle, just as electrons never sit idle, but constantly emit and reabsorb virtual photons, so nucleons are not inert, but constantly emit and reabsorb their own type of virtual particles. A nucleon is a proton or a neutron. Both of these particles are called nucleons since both of them are found in the nuclei of atoms. They are so similar to each other that a proton, roughly speaking, can be considered as a neutron with a positive charge. Yukawa knew the range of the strong force from the results of published experiments, assuming that the limited range of the strong force was identical to the limited range of a virtual particle emitted from a nucleon in the nucleus. He calculated how much time such a virtual particle would require at close to the speed of light to go that distance and return to the nucleon. This time calculation allowed him to use the uncertainty relation between time and energy to calculate the energy, mass, of his hypothetical particle. 12 years and one case of mistaken identity later, physicists discovered Yukawa's hypothetical particle *. They called it a meson. An entire family of mesons, it later was discovered, are the particles which nucleons exchange to constitute the strong force. The particular meson which physicists discovered first, they called a pion. Pion is short for pi, pronounced pi. Meson pions come in 3 varieties: positive, negative, and neutral. In other words, a proton, like an electron, is a beehive of activity. Not only does it continually emit and reabsorb virtual photons, which makes it susceptible to the electromagnetic force, it also emits and reabsorbs virtual pions, which makes it susceptible to the strong force as well. Particles which do *\V. Hen the muon was discovered in 1936. It looked like Yukawa's predicted particle. Gradually, however, it became evident that the muon's properties were not those of that particle in Yukawa theory. Another 11 years passed before Yukawa's theory was confirmed. The *229 not emit virtual mesons, like electrons, for example, are not affected at all by the strong force. When an electron emits a virtual photon which is absorbed by another particle, the electron is said to be interacting with the other particle. However, when an electron emits a virtual photon and then reabsorbs it, the electron is said to be interacting with itself. Self-interaction makes the world of subatomic particles a kaleidoscopic reality whose very constituents are themselves unceasing processes of transformation. Protons, like electrons, can interact with themselves in more ways than one. The simplest proton self-interaction is the emission and reabsorption, within the time permitted by the uncertainty principle, of a virtual pion. This interaction is analogous to an electron emitting and reabsorbing a virtual photon. First there is a proton, then there is a proton and a neutral pion, then there is a proton again. Below is a Feynman diagram of a proton emitting and reabsorbing a virtual natural pion. 70. Because all protons are identical, we can assume that the original proton suddenly ceases to exist and that, at the same point in space and time, another proton and a neutral pion just as abruptly come into existence. The new proton and the 230 / I clutch my ideas. Neutral pion constitute a violation of the conservation law of mass energy, since their mass together is greater than the mass of the original proton. Something, the neutral pion, literally has been created out of nothing and quickly disappears again, making this a virtual process. The lifespan of the new particles is limited to the time calculated via the Heisenberg uncertainty principle. They quickly merge, annihilating each other, and create another proton one blink of an eye, figuratively speaking, and the whole thing is over. There is another way in which a proton can interact with itself in addition to emitting and reabsorbing a neutral pion. A proton can emit a positive pion. However, BV emitting a positive pion, the proton momentarily transforms itself into a neutron. First there is a proton, then there is a neutron, which by itself has more mass than the original proton, plus a positive pion, then there is a proton again. In other words, one of the dances that a proton does continually changes it into a neutron and back into a proton again. Below is a Feynman diagram of this dance. Every nucleon is surrounded by a cloud of virtual pions, which it constantly emits and reabsorbs if a proton comes close enough to a neutron so that their virtual pion clouds overlap. Some of the virtual pions emitted by the proton are absorbed by the neutron. On the next page is a Feynman diagram of a virtual pion exchange between a proton and a neutron. The dance /231. In the left half of the diagram, a proton emits a positively charged pion, momentarily transforming itself into a neutron. Before the pion can be reabsorbed, however, it is captured by a nearby neutron. This pion capture causes the neutron to transform itself into a proton. The exchange of the positive pion causes the proton to become a neutron and the neutron to become a proton. The two original nucleons, now bound together by this exchange, have changed roles. This is the basic Yukawa interaction. The strong force, as Yukawa-theorized in 1935, is the multiple exchange of virtual pions between nucleons. The number of the exchanges, the strength of the force, increases at close range and decreases at a distance. In a similar manner, neutrons never sit still and just be Neutrons like protons and electrons THEV also constantly interact with themselves by emitting and reabsorbing virtual particles like protons. Neutrons emit and reabsorb neutral pions. On the top of the next page is a Feynman diagram of a neutron emitting and reabsorbing a neutral pion. In addition to emitting a neutral pion, a neutron also can emit a negative pion. However, when a neutron emits a negative pion, it momentarily transforms itself into a proton first. There is neutron, then there is a proton plus a negative pion. 232 / I clutch my ideas. IT. Then there is a neutron again. Below is a Feynman diagram of this dance with continually changes a neutron into a proton and back into a neutron again. If a neutron comes so close to a proton that their virtual pion clouds overlap, some of the pions that are emitted by the neutron are absorbed. BV. The proton below is a Feynman. The dance / 233 diagram of a virtual pion exchange between a neutron and a proton. This is another strong force interaction in the left half of the diagram. A neutron emits a negative pion, temporarily transforming itself into a proton. However, before the negative pion can be reabsorbed, it is captured by a nearby proton, which, in turn, becomes a neutron. The exchange of a negative pion causes a neutron to become a proton and a proton to become a neutron. As before, a pair of nucleons, bound together by a virtual pion exchange, have changed roles. There are more strong force interactions, although pions are the particles most often exchanged in the succession of the strong force. The other mesons, such as kaons, eta particles, etc., are exchanged as well. There is no strong force. There are only a varying number of virtual particle exchanges between nucleons. 77. The universe, according to physicists, is held together by 4 fundamental types of glue in addition to the strong force and the electromagnetic force. There is the weak force and the gravitational force. Recent evidence GI/S Jonk credence to the Wemby-Salam theory that electromagnetic and weak forces are actually different manifestations of the same force operating at different distances between particles. 234 / I clutch my ideas. Gravity is the long-range force which holds together solar systems, galaxies, and universes. However, on the subatomic level its effect is so negligible that it is ignored altogether. Future theories, hopefully, will be able to take it into account. The weak force is the least known of the 4 forces. Its existence was inferred from the times required by certain subatomic interactions. The strong force is so short-range and powerful that strong force interactions happen very fast. In about 0.0000000000000000000001, Mr. 23 seconds. However, physicists discovered that a certain other type of particle interaction which they knew involved neither the electromagnetic nor the gravitational forces, required a much longer time, about 0.000000000110 seconds. Therefore deduced from this strange phenomenon that there must exist a 4th type of force, since this new 4th force was known to be weaker than the electromagnetic force. It was called the weak force. In the order of their strength, the four forces are: strong, nuclear, forte, electromagnetic force, weak force, gravity. Since the strong force and the electromagnetic force can be explained in terms of virtual particles, physicists assume that the same is true of the weak force and gravity of the particle. Associated with gravity is the graviton, whose properties have been /ed, but whose existence never has been confirmed. The particle associated with the weak force is the W particle, about which much has been /ed, but not much has been discovered. The range of the strong force, relative to the electromagnetic force, is limited because mesons, relative to photons, have so much mass. Remember that the policeman who enforces the conservation law of mass energy is willing to turn his back if the violation is quick enough, but the more flagrant the violation, the more quickly it must happen. The momentary creation of a meson out of nothing is a much more flagrant. Teg supergravive theories that me both spin 2 and spin 3 /2 /Urchul exchange particles. The dance /235. Violation of the conservation law of mass energy than the momentary creation of a photon out of nothing. Therefore, the creation and reabsorption of a meson must happen more quickly to stay within the protection, so to speak, of the uncertainty relation between time and energy. Because the lifespan of a virtual meson is limited, its range also is limited. The rule of thumb governing this phenomenon is this: the stronger the force, the more massive is the mediating particle, and the shorter is its range. The range of the strong force is only about 1/10,000th, 10 of a centimeter accordingly, the range of the electromagnetic force is much greater than the range of the strong force. In fact, the range of the electromagnetic force is infinite. This is because photons don't have any rest mass. Wait a minute, says Jim DeWitt, agreeing with us for a change. This doesn't make sense. A virtual photon is a photon which is emitted and reabsorbed quick enough to avoid violating the conservation law of mass energy. Right, says a particle physicist on his way to the cyclotron. Then how can a particle, or anything else, be emitted and reabsorbed within certain time limits, like the time limits imposed by the uncertainty principle, and still have an infinite range? It doesn't make sense. DeWitt has a point. At first glance it appears that he is correct. On closer examination, however, there be a subtle logic involved which affos make sense if the limitations of the conservation law of mass energy are avoided by a balance of time and energy, mass, permitted by the uncertainty principle. And a /Urchul photon has no rest mass, then it has all the time in the world, literally to go where it pleases. In other words, there is no practical difference between a real photon and a virtual photon. The only difference between them is that the creation of a real photon does not violate the conservation law of mass energy, and the creation of a virtual photon avoids this law momentarily via the Heisenberg uncertainty principle. This is a good example of how unreal and ivory tower, like the non-mathematical explanation of a successful physical theory, can sound. The reason for this is that physical theories, in order to describe more accurately the phenomena under consideration, have become more and more divorced from everyday experience, i.e. more abstract, although these highly 236 / I clutch my ideas. Abstract theories, such as quantum theory and relativity, are unaccountably accurate to an awesome degree. They truly are free creations of the human mind. Their primary link with ordinary experience is not the abstract content of their formalisms, but the fact that, somehow, they work. The distinction between a transient, virtual, nothing nothing, state and a real one, something, is similar to the Buddhist distinction between reality, as it actually is, and the way that we usually see it. For example, Feynman himself described the difference between a virtual state and a real state, of a photon, as a matter of perspective. What looks like a real process from one point of view may appear as a virtual process occurring over a more extended time. For example, if we wish to study a given real process, such as the scattering of light, we can, if we wish, include in principle the source, scatterer, and eventual absorber of the scattered light in our analysis. We may imagine that no photon is present initially, and that the source then emits light. The light is then scattered and eventually absorbed. From this point of view, the process is virtual, that is, we start with no photons and end with none. Thus we can analyze the process by means of our formulas for real processes by attempting to break the analysis into parts corresponding to emission, scattering, and absorption too. According to Buddhist theory, reality is virtual in nature. What appear to be real objects in it, like trees and people, actually are transient illusions which result from a limited mode of awareness. The illusion is that parts of an overall virtual process are real, permanent things. Enlightenment is the experience that things, including I, are transient virtual states devoid of separate existences, momentary links between illusions of the past and illusions of the future unfolding in the illusion of time. Particle self-interactions become quite intricate when virtual particles emit virtual particles which emit virtual particles in a Paul Behilp, ed. Albert Einstein, philosopher scientist / 1 New York. Harper and Row 1949 has some G.X.D. essays on this theme. The dance / 237. Diminishing sequence below is a Feynman diagram of a virtual particle, a negative pion, transforming itself momentarily into two more virtual particles, a neutron and an antiproton. Dirac's 1928 theory also predicted antiprotons, which were discovered at Berkeley in 1955. This is the simplest example of self-interaction. On page 238 is the exquisite dance of a single proton performed in the flicker of time permitted by the uncertainty principle. This diagram was constructed by Kenneth Ford in his book, The World of Elementary Particles. 311 particles make their transient appearance between the tune. The original proton transforms itself into a neutron and a pion, and the time it becomes a single proton again. A proton never remains a simple proton. It alternates between being a proton and a neutral pion on the one hand, and being a neutron and a neutral pion on the one hand, and neutron never remains a simple neutron. It alternates between being a neutron and a neutral pion on the one hand, and being a proton and a negative pion on the other hand. A negative pion never remains a simple negative pion. It alternates between being a neutron and an antiproton on the one hand, etc., etc. In other words, all particles exist potentially. 0. I. TT. 238 / I clutch my ideas. With a certain probability, as different combinations of other particles, each combination has a certain probability of happening. Quantum theory deals with probability. The probability of each of these combinations can be calculated with accuracy. According to quantum theory, however, it is ultimately chance that determines which of these combinations actually occur. The quantum view that all particles exist potentially as different combinations of other particles parallels a Buddhist view. Again, according to the Lower Sutra, each part of physical reality is constructed of all the other parts. A sutra is a written account of the Buddha's teachings. This theme is illustrated in the Flower Garland Sutra by the metaphor of Indra's net. Indra's net is a vast network of gems which overhangs the palace of the god, Indra. The dance / 239. In the words of an English interpreter, in the heaven of Indra, there is said to be a network of pearls, so arranged that if you look at one you see all the others reflected in it. In the same way, each object in the world is not merely itself but involves every other object, and in fact is everything else, for the appearance of physical reality according to Mahayana Buddhism is based upon JUE interdependence of all things *t. Although this book is not about physics and Buddhism specifically, the similarities between the two, especially in the field of particle physics, are so striking and plentiful that a student of one necessarily must find value in the other. Now we come to the most psychedelic aspect of particle phys. ICS below is a Feynman diagram of a three-particle interaction. In this diagram no world line leads up to the interaction, and no world line leads away from it. It just happens. It happens literally out of nowhere for no apparent reason, and without any apparent cause where there was no thing. Suddenly, in a flash of spontaneous existence, there are three particles which vanish without a trace. Asterisk from discussions with Professor John Blefeld, a Buddhist and Taoist scholar. I believe that there are even better illustrations of this concept in the Flower Garland Sutra than the metaphor of Indra's net, the Flowerkarita Garland Sutra, which also is called the Hualen Sutra, Chinese, and the Avatamsaka Sutra, Sanskrit, is extremely long. A complete translation with commentary would be about 150 volumes. At the time of this printing there is no complete English translation of the Plotter Garland Sutra, although one is in progress. BV the Buddhist Text Translation Society, City of 10,000 Buddhas, Talmage, California 95481. TGF2SI Bootstrap theory may be a physical analog to the Buddhist theory of interdependent originations. 240 / I clutch my ideas. This type of Feynman diagram is called a vacuum diagram *. That is because the interactions happen in a vacuum. A vacuum, as we normally construe it, is a space that is entirely empty. Vacuum diagrams, however, graphically demonstrate that there is no such thing. From empty space comes something, and then that something disappears again into empty space. In the subatomic realm, a vacuum obviously is not empty. So where did the notion of a completely empty, barren, and sterile space come from? We made it up. There is no such thing in the real world as empty space. It is a mental construction, an idealization, which we have taken to be true. Empty and full are false distinctions that we have created, like the distinction between something and nothing. THEV are abstractions from experience which we have mistaken for experience. Perhaps we have lived so long in our abstractions that instead of realizing that they are drawn from the real world, we believe that they are the real world. Vacuum diagrams are the serious product of a well-intentioned physical science. However, THEV also are wonderful reminders that we can intellectually create our reality. It is not possible, according to our usual conceptions, for something to come out of empty space, but, at the subatomic level, it does, which is what vacuum diagrams illustrate. In other words, there is no such thing as empty space, or nothing, except as a concept our categorizing minds. The core sutras of Mahayana Buddhism, the type of Buddhism practiced in Tibet, China, and Japan, are called the Prajnaparanta Sutras. Among the most central of the Prajnaparamita Sutras, there are 12 volumes of them, is a sutra which is called simply, the Heart Sutra. The Heart Sutra contains one of the most important ideas of Mahayana Buddhism. Form is emptiness, emptiness is form. Bnan Josephson, Jack Sarfati and Nick Herbert independently have speculated that human sense-of systems might detect the zero-point vacuum fluctuations OT. The dance of /virtual particles in empty sparked predicted by the uncertainty principle. If this is so, such detections might be part of the mechanism of mystic knowing. Prajna, Sanskrit, means wisdom, but it is a special kind of wisdom which cannot be learned through studying books. Paranta, Tyali, to cross over, means bringing something to perfection. The dance /241. Below is a vacuum